Já. you could show it to people.
Hello, everyone. Welcome to the second day. Hope you had a nice day yesterday and everything is going smooth for you. Hope you are enjoying Terceira Island. Today we'll have a very interesting day. We'll start with star data manipulation, and we'll also do hands-on session on data visualizations with Makie. And to start, we'll get a presentation from Felix Cremer. Felix Cremer received his diploma in mathematics from the University of Leipzig in 2014. In 2016, he started his PhD study on time series analysis of hypertemporal Sentinel-1 radar data. He is interested in the use of irregular time series tools on synthetic aperture radar data to derive more robust information from these data sets. And he worked on the development of deforestation mapping algorithms and on flood mapping in the Amazon using Sentinel-1 data also. He currently works at the Max Planck Institute for Biogeochemistry on the development of Julia Data Cubes ecosystem in the scope of the FDI for Earth projects. The Julia Data Cubes organization provides easy to use interface for the use of multidimensional raster data. Thank you, Felix.
Thank you. Yeah, good morning also for me. So for the session now, I'm going to give a very broad overview of our introduction into synthetic aperture radar, because we're hearing a lot more about the processing of it later today, and also having a hands-on session on change detection with this data set. So the most important thing about the synthetic aperture radar is that it's an active sensor in contrast to a passive sensor. So the passive sensors are like all of the optical satellites. They acquire the light that is reflected from the Earth, which is coming from the sun. And so you have the sun as the source, and then you just have a receiver at the satellite. In an active system, you have a source of microwave in the case of Sentinel-1, and then you acquire what's coming back. Other active remote sensing techniques are LiDAR data, for example. And then so this is what this looks in for real data. So this is on the left Sentinel-2 image of the Terceira Island, and on the right the Sentinel-1 image at roughly the same dates. On the optical data, you see you can clearly distinguish the sea. Then you can also see the agricultural areas. You see we have a mouse here. No, it's not working. So you see forest areas here, and you also see some of the urban structures. In the SAR image, it's a bit getting used to looking at that. So you also see the open water as clear black areas, but in the ocean you also have roughness effects on the waves. And then you can see the urban structures in white. You can clearly see the airport because it's a very smooth surface. And I'm going to go into more detail why we see what we're seeing here. but you can't as easily see the differences between the agricultural and the forested areas. So why do we even bother to look at this data? There are clouds, and this is just the average cloud cover of November last year. And so every area that is purely white is just fully clouded for months. And so you have a lot of areas where you can't acquire any data, or you also can't, or you only have some data at some parts of the year. And with SAR data, you can acquire data on a regular basis because it's able to go through the clouds because it's using microwave data instead of the optical wavelengths, and also it's able to acquire data on the Arctic, for example, during wintertime, which is not possible in optical data. So SAR data has been used since the 1970s. So the first actual SAR satellite was the CSAT mission by NASA in 1978. Then there have been 3 space shuttle missions, of which the SIR-C mission acquired the data for the SRTM global elevation model. And then in the 1990s, the ESA started to launch the EIS-1 and 2 satellites. Then the Canadians started to launch RadarSats. Germany started the Tandem X missions in the beginning of 2000s. Japan has a long tradition of using L-band data, and then with the launch of Sentinel-1, I think we reached a new era of SAR data, because now we have a continuous acquirement, so a continuous acquisition of C-band data on a regular basis. So they try to cover the whole Earth and some parts of the Earth on a much more regular basis, but at least every part of the world once or twice a year. And then also they're starting to get private companies like ICE-Eye that started also a few years ago, and there are new satellites planned like the Biomass mission, the NISA mission, or ROSE-L. So the Sentinel-1 data is like, this is the global coverage map of Sentinel-1 data that is available. So you can clearly see it's a European focus because it's European funded, but also you have a lot of acquisitions on different parts of Africa, different parts of Asia, also the whole Greenland and parts of the Antarctic. Yeah, it's basic. I mean, the maximum number of images is 1,600 images in the last 7 years, and so it's nice that it's just going to be repeatedly acquired. So to talk a bit about the acquisition mechanism of SAR, so it's a side-looking radar, so it's not looking down like an optical satellite, but it's looking in an angle of 25 to 45 degree, and you have differences in the near range and the far range, but I'm not going to go into detail here because I think this will be covered in the afternoon by the SAR processing plenary. But with this side-looking acquisition mode, you get some geometric distortions that you need to be aware of. So if you have a high mountain, you could have shadows in the image because you can't reach what is behind the mountain. You can have foreshortening. This just means that the slope of the mountain that is turning back away from the satellite is appearing larger in the SAR geometry. So it's like these two slopes have the same lengths in the actual geometry on Earth, but in SAR one is shorter than the other, and therefore on this pixel there's much more. This would be much brighter because it's getting more energy from the same area on Earth. And then you can have an extreme case of this foreshortening where you acquire the tip of the mountain before you acquire the bottom. And then basically your mountains look like they are flipped a bit. And so these are examples. So I would like you to shortly think about what could be what in these effects. And so the foreshortening is these brighter appearing areas here, which are just that's just a bit brighter. Then the shadows are easily distinguished as very dark areas where it shouldn't be that dark because there's no water or no other reflectance. And then you have the layover, which is just these smoothing of the mountain areas. And so with this SAR, you have also different, you can have different scattering principles. So the first one is just rough surface reflectance on some open area. So that would be A. So you send the microwave is sent on the surface, then you have some scattering process, and most of the energy is just randomly distracted somewhere, and then parts of it is coming back. Then in B you have a double bounce between the surface and some natural structures. So this could happen, for example, at the edge of deforested areas or generally at the edge of the forest, where you have a bit more backscatter because you first hit the smooth looking trunk of the tree, and then you hit the ground, and then you get a bit more back than in the rough surface. This would be much more pronounced in urban areas. That's why these urban areas are showing up as very bright areas, because you have man-made structures which are very smooth, and then we also have smooth concrete on the ground, and therefore you have this double bounce effect where a lot of energy is reflected back to the SAR signal to the satellite. And you can basically have the same if you would have standing water beneath the canopy or at the edge of the canopy. And then you also have the so-called you can have the so-called volume scattering. So you can, depending on the wavelengths that you're working with, either have a scattering mechanism directly on top of the canopy, like in D, or you can have interactions between the microwave and the canopy cover inside of the canopy, and then you can have a bit. You also get random reflections, but you get a higher backscatter value than on the rough surfaces. Then another distortion that you should be aware of is that these images are looking a bit noisy because they are this is the so-called speckle effect. And this is because you have a coherent system that is sending the microwaves in all the same phase. And then you have random interactions. So this is how this looks if you zoom in. So it's in one agricultural field where the surface is actually the same, but you can have random effects from the phase, which would then induce this. And so the reason is that you send down your signal, and then the signal interacts with the scatterers, and then because you have a much larger area than your wavelength. So the wavelength is in a range of a few centimeters to maximally a meter, and then you have multiple scatterers that are going back that are sending the signal back to your satellite, and then because it's a complex signal, so you have a phase, and then so you have an real and an imaginary part, and then you basically sum all of these different scattering processes together to get your final results, or to get your final and then you can compute the amplitude from that. But because these phases can be different depending on whether some scattering process is happening here or here, you get these random shifts, and then the sums can be either very high or very low, and therefore you have these random looking differences between pixels on the same land surface. And then to deal with that, you could use a speckle filter. So I'm not going to go into much detail, but we also did a study on that because normally you can either do so-called multi-looking by averaging in different neighboring pixels. So you're smoothing the image, thereby reducing your spatial resolution. And then there are ways to mix this and to have a spatial average and a temporal average. And we did a study on only using the temporal information, because with Sentinel-1 we have a very high repetition rate. So we have an image every 12 days, and then we can use this temporal information to also smooth the data. And we showed that we get a similar smoothing to other techniques, but without losing spatial information. So might be interesting, or so it depends on the use case whether it could be useful to use. And then another thing to know about is the so-called polarization. So you can have the wave either going vertically, so either moving up and down, or it's moving horizontally. And this influences how the SAR signal interacts with the land surface. And basically the satellites that are in orbit can either send the data vertically or horizontally, and then some of them can then acquire the backscatter also in vertical or horizontal. And Sentinel-1 can only acquire so Sentinel-1 can send both polarization types, but it can only send one at the same time, and then acquires the same and then acquires the vertical and horizontal together. So therefore it's a so-called dual polarized satellite. And then, but there's also quad pole systems that can send both polarizations at the same time, and then receive both, and then derive more information from that. It's just to give a short idea of what might be the differences between the polarization. So on the left, it's the VV data again, and on the right, it's the VH. So it's both vertically sent and then received vertically or received horizontally. And you can see that the VV image is brighter in general. You have a you see more of the man-made structures like this, or also here in Anga do Heroísmo. And but then on the other on the VH, you see a bit more the differences between the agricultural areas here, and you can see certain patches of different agricultural fields, and then you also see patches of forest areas. And then you can also combine these in making a RGB image of the VV, the VH, and the ratio data to derive even more structure from it. And so you see some mountain range here. You see the volcano, and also here you see more differences between the different fields or different agricultures. And another thing that changes the acquisition of the or that changes how your image looks is the wavelength, as I said. So it's from a few centimeters. So the X band, like in tandem X, is 3 centimeters. The C band in Sentinel-1 is like 6 centimeters, and the L band is 20 to 30, depends a bit on the satellite. And then you have the P band, which is now going to be sent into space in the ESA biomass mission, which is at 70 centimeters. And so the rough idea to work with these different wavelengths is that you can imagine that the microwave is interacting with everything that is at least as long as the wavelength. So with X band, you have an interaction only with things that are shorter than, or you can penetrate only through things that are shorter than 3 centimeters. So therefore, that's why in the forest you would interact directly with the canopy cover, or with the top of canopy. With C band, you interact with everything that is 6 centimeters. Then you have you can go through a bit of the forest. You can go through some of the other vegetation types, like grasslands and wheat and so on. With L band, you can go basically, the signal goes through the whole forest canopy and then interacts with most of the stem structure and some of the branches. And in P band, you only see, or the satellite sees only the overall trunks and stems and larger things that are there, and it's not interacting with all of the leaves and all of the small branches. So I just wanted to also shortly mention a few use cases that SAR data is used. So there's a lot of interaction with soil moisture, because the SAR signal not only depends on the geometry, but it also depends on the dielectric properties. So in natural areas, that basically means, is there water or is there no water? And human structures, this could also mean, is there a metal plate somewhere, because the microwave is just going to interact with the metal or with other man-made structures like windmills or power lines. And then you have a surface water dynamics use cases, because on top of undisturbed water, you have a clear reflectance going back from the sensor, and thereby the open water areas are appearing as clear black areas in your image. Then you also have a large community using that for sea ice and also for glacier monitoring, but I'm not really I don't have any deeper knowledge about that. Then it's also used for above ground biomass detection. It's used for ship detection. The phase information can also be used for ground motion and just small changes in the small movements in the ground. And we can also use it for change detection. And just to give some real life examples that I found online are, for example, flood mapping based on for the typhoon in Africa a few years ago. So the flooded area is basically shown in red, and this information is derived of multiple Sentinel-1 images. And then there's also maps of above ground biomass derived from L-band data, and also a lot of work on doing ship detection and using this to track ships in the open ocean. Yeah, and that's the end of my presentation, and I'm open for questions. Yes?
I was wondering what the pattern of sampling that was shown in the global map, that there's and I'm sort of assuming that because there's an energy source that's needed, so they only trigger satellite, or maybe because we transmit the data, like an on switch that
you mean this? Yeah. Yeah, so there's basically two things hindering more coverage. One is you need energy for the SAR data, right? You need a lot more energy than in an optical satellite, because you need to send the signal from the satellite. But I think, I'm not entirely sure, but I think even more importantly is the downlink. You need to then get the data down to Earth. And you saw that this was a huge problem because a few years ago, I think in 2018, ESA launched the data relay satellite. So basically you have your Sentinel-1 going here, and then you need to fly over a ground station to get it downlinked to Earth. And instead of that, you have another satellite that is somewhere else, that is then seen from Sentinel-1, which downlinks that to some of the ground stations. And that, I mean, I'm not sure what currently are the main restrictions, but at least from looking at the time series data of Sentinel-1 that I worked with, you saw a clear increase of available data somewhere in 2018.
guess I'll ask another one. I'm assuming on the ocean side, the detection of the wave and the roughness of the sea. What sort of scale range does that include?
Unfortunately, I can't. I would need to look it up. I don't have any experience with working with SAR on sea.
Okay.
So
No worries. Thank you.
should we just wrap it up then? And we have a coffee break now, right?
Thank you, Felix. Yes, Felix is right. We are now having a coffee break until 5:10. Yes. I will also like to ask if someone is the owner. Okay, I'll give it to you. Then we come back at 5:10. Okay. Thank you. Okay, hi again. Is everyone ready to start? Okay, sorry, I didn't introduce myself in the beginning. For those who don't know me yet, I'm Mariana, and I work at the Air Center in the EO lab. In the present, I'm doing a PhD in University of La Laguna, and I'm using remote sensing data to infer about quality of the pastures here in Terceira Islands and trying to correlate to a phenomenon related to sporulation of a fungus that has an high impact on the life of the cows here. So to continue, we'll now have a hands-on session on data visualizations with Makie. And we'll start with Simon Danisch. Simon is the author of Makie and currently works full-time on Makie as a freelancer. He has been part of the Julia community for more than 10 years and is the author of many Julia packages. To just name a few, there are still actively used by many people on the Julia community: the Makie, geometry basis, GPU arrays, package compiler, JServe, and FilO. His mission has always been to create a sustainable plotting and graphics ecosystem for Julia, which enables visualizations in need of high performance, as well as making it very easy to quickly create simple plots and integrate them into dashboards. Nowadays, with climate change threatening to destroy the fundament of our modern life, he is focusing his efforts on making sure that Makie works well for climate science to better understand the changes that are coming to us. After Simon, we'll have visualization of Earth observations data by Lázaro Alonso, and is a Mexican physicist currently working at the Max Planck Institute for Biogeochemistry in the Model Data Integration Group. He is interested in hybrid model-based approaches to climate science, as well as scientific visualizations. Other interests of his are complex networks, graph neural networks, and time series analysis. He is also co-author of the Julia Data Science book and main contributor to the gallery beautifulmakie.org, and contributes as much as possible to open source in his spare time, if any. Okay, thank you.
Thank you. Yeah, this is a Makie hands-on. I decided not to give like a very basic introduction to Makie, but instead show off some cool new features I've added for the web-based backend. But yeah, I still wanted to have a little bit of an introduction to Makie here and talk a bit about what it is. So it's a plotting framework, mostly written in Julia. I guess from its scope, it's a bit comparable to matplotlib or any other plotting library like that. It has a bit more focus on interactivity and visualizing large data in 3D than other plotting libraries. And it has this kind of backend system to support multiple use cases very well. So on a desktop with a GPU, you want to use GLMakie for high performance visualization. If you're wanting to turn your plots into a publication, there's ChairoMakie, which helps you export vector graphics like PDF and SVGs. And then for the web, there's WebGL-Makie that's based on WebGL, like in the name. And there's a experimental ray tracing backend, which is really nice for creating stunning high fidelity visualizations. Yeah, it works for 2D and 3D. And I just inserted the cheat sheet from Lázaro, which I think should give you a very quick overview of like the scope of Makie, what it's like able to do. It should be animated, I guess, to really show the full scope, because yeah, as I said, quite a bit of focus in Makie is that it's easy to interactively visualize things. There's quite a bit of an ecosystem around Makie, also because it's kind of designed that Makie is like the core tool with a relatively low-level API, and that other people then write their own packages to make it easier to use in different domains. So, for example, there's algebra of graphics, which gives Makie a kind of ggplot interface to make it much easier to do statistical plotting. There's GeoMakie, which is not as stable as other packages, but it's a start. And I hope starting here with all the Geo people, we can figure out a way to maintain it a bit better. But I will actually use it in the talk to make a little Earth visualization. We already mentioned the great website from Lazaro with a ton of incredible examples that should really help to see how to create beautiful plots with Makie. And there are quite a few more little things, like Graph Makie is pretty well maintained, I think, at this point. And you can make pretty amazing visualizations with it. Wait, there's some pretty cool ones, like where you can just animate graphs and interact with them. And I think it also has like a graph editor where you can move around the edges and stuff like that. There's also one that builds upon Graph Makie. So like already like a second layer above Makie for visualizing street data, OSM data, which has been seeing quite a bit of improvements since the last time I checked. I don't think it had this fancy menu here before. And yeah. And the docs, obviously. So they're all under this umbrella of the Makie.org domain. But yeah, I think to really get started, the first steps in Makie and how it works, one should just look into the docs, and I will concentrate on showing a finished plot and some cool stuff around it that I've recently developed. But I also wanted to talk a bit about the backends, because it's fairly unique, I think. So Makie itself, the package, just defines a backend independent language, you could say, to specify how the plot should look, and then the backends actually draw it. And GeoMakie is the first backend that I developed. It has a lot of code inside that's very old from my beginnings in Julia, where I dabbled with OpenGL and high performance visualizations and 3D animations. It has quite a few basic UI elements, which are quite usable at this point. So you can make little simple dashboard to explore your data completely inside a desktop window. Yeah, but it does need a GPU, so it's not usable for all use cases, even though you can set up a virtual GPU on most headless servers or anything like that. But you might want to use a different backend in those cases. Makie uses Cairo to draw this Makie plots as vector graphics. It has very high 2D rendering quality because it doesn't have the speed requirements that GeoMakie has. So it has a bit better anti-aliasing and things like that. And yeah, you can export it to PDFs and put it in your publications directly. It also is able to do 3D plots, but it's a bit experimental. There are a few things that don't work as well, like in the other backends, because yeah, we need to do our own 3D drawing inside a format like PDF that's mostly for 2D or SVG actually. Yeah, but it runs everywhere, runs on the CPU. So it's, I think a lot of people use it as their default backend because it's also a bit faster to start and things like that. WebGL Makie is the, after RPR Makie, it's the latest backend that I added. It creates visualizations in the browser via Three.js and WebGL. So part of it are written in JavaScript, but it also uses a large part of Makie, which is written in Julia. It works quite similar to GL Makie because it's also based on WebGL, and Makie is based on OpenGL, which are related, which is basically just the browser API to do things on the GPU. So it can actually be fast for visualizing a lot of data, but animating it is a little bit slower because you need to serialize the data in Julia, send it to the browser, and then deserialize it in JavaScript, which is quite a bit of overhead depending on your data. It's pretty feature complete, but there are a few random things that are just not implemented right now because I didn't have the time for it, like marker strokes and line joints. It's a bit random, but that's how it is. Because the browser takes care of running everything on the GPU and always having a fallback if you don't have a GPU. I think it runs almost anywhere. And yeah, so it's great for working if you have a huge simulation on a server that doesn't have a GPU and you want to interact with it on your local machine, then WebGL Makie is a great tool. And the ray tracing backend is very new. It's pretty much just a prototype, I'd say, at this point. Mostly just supports the 3D primitives of Makie. Sadly, it only runs on Linux and Windows right now, which I hope might be solved by just upgrading the dependency. It's very slow, but that's part of ray tracing. That's just a very slow process. So, but that means you need high-end hardware for high-quality animations. I think on a 380, so a pretty recent fast GPU, it can take up to 30 seconds to create a nice looking image. But yeah, if it works, it looks pretty nice. And I hope it can be used in the future to make really nice looking visuals of some interesting data sets. Yeah, I want to concentrate on WebGL Makie because I just improved it a lot in the recent months, and the capabilities to use it for making dashboards. And yeah, I just realized I kind of skipped the hands-on part. So we tried to prepare Docker images and the data set, and we iterated over it quite a bit, and now it's a bit confusing. So I decided we'll just upload one good way to do it in the end, and nobody needs to follow it live. If you already have it running, of course, feel free to follow it and play around with it. But yeah, I won't explain how to set it up right now. So I want to show off a visualization I made for the climate machine for their simulation data of the Earth and atmosphere. It looks like this. Oh, it's a bit cut off. Can we? Why is there such a large gap here? Oh yeah, that's better. So here, this is a 3D visualization of the same data just on a sphere. It has multiple levels in the height of the atmosphere. It has it's a time series, so of the simulation. It has multiple fields like pressure and things like that. And yeah, I want to introduce you to this observable concept here, which is the main way, one of the main ways in Makie to create interactive graphs. Basically, what you can already see here is that there's this one simulation plot function that takes all these observables here. And the concept of observable is relatively simple. It's just like wrapping a value, and then you can register on the updates to that value. So whenever you update a value in Makie, I can register, I can run functions on every update. So if I update this here, you see I changed the field, I changed the level and the time, and now the plot updated. And this is a very fast way of updating things, because, for example, in a lot of plots of large data, you might want to change the color, but it's or the positions of particles or something like that. And updating the positions of particles is kind of expensive, but for example, changing the color can be very cheap. So you want to have them separated. And by using these observables for the color, for the position, or for the field, or things like that, you can kind of separate these and update them like more surgically. I think a lot of other plotting frameworks have gone down the road to just replot everything. So basically, instead of passing in observables here, they would just call the simulation plot functions every time something changes and start from scratch, basically, which is for large data can be a lot slower depending on what you need to do. But yeah, so I wanted to give a quick start with how you use observables. So you already saw, you can just construct it for the value that you want to pass. And then you can map over the updates and get back a new observable of a function that gets applied to the new value. So this observable that you get here will always be this observable +1. And you can also just register a function on any update of +1, for example, without creating a new observable with the on function. And if you update another observable inside this on function here, it's pretty much the same as the map functionality, but that's what you use if you don't actually want to create a new observable. And then there's also this connect function that I will be using, where you can connect one observable with the other and forward all the updates to the other observable. Yeah.
So since it's hands-on,
Sure.
It's okay. I was wondering, I used to write this with a @lift macro, I think, something.
Oh yeah.
To that effect. So this would be a new, better way to do this.
Actually, it's kind of the other way around. So Julia's introduced the lift macro as a convenience function, so it's newer. But I'm kind of old school, I guess. I just use the map directly. That's the so this comes from observables.jl, and this is the original API from observables, and the lift macro was added to Makie. So Julius just added it to Makie, and I think it's a bit nicer and more terse to write, but it can also be confusing to people that don't know the macro. So if you're reading the code, but I don't know, maybe the map is also confusing to people. But just to show you how it would be done with the lift macro. So this is just like the inside of the function basically, and you can write it more directly. And any observable in there needs to be interpolated here with this sign. But you can also use other variables that are not observables if you don't use the sign here. So if you would do this, it wouldn't work, because then it would just make 1 plus the observable, and the observable doesn't have any function like plus overloaded. Yeah. So yeah. That's true. Yeah, I'm not too happy with that situation. Inside Makie, I use lift everywhere, because it's easier to refactor, because map is such a generic function that can be anything, and lift is really just for observables, so it makes it easier to immediately see. But yeah, for this talk, I just wanted to stick to the observable basic API. Yeah, so JSServe is a package I've written to create WebGL Makie. So it's a package that allowed me to communicate with JavaScript, and actually implement that you can pass observables across the language borders. So JSServe basically is a framework with observables at its heart, where you can just pass them into an HTML or JavaScript DOM, and it will update in JavaScript. So this way you can register on the JavaScript side, you can register to these updates. And JSServe also makes it very simple to create HTML DOMs and insert some JavaScript in there. I just made a very small example here. Here you can see that, yeah, DOM gives you all these HTML tags. So if you're familiar with HTML, this should be very simple to start with. Of course, the syntax is a bit different because we can't just copy the HTML syntax directly in Julia. So it's having this kind of, yeah, function syntax here. But the keywords should be all the same that you can pass, and they should directly end up in the HTML like expected. Yeah, so just to make something bold, you could use CSS or directly pass this HTML style attribute. And did I run this? Yeah. And yeah, JSServe also already wraps a few of the HTML standard widgets, like the range input, which I usually call slider. I think it's kind of funny in HTML terms, slider is usually a slideshow of images. And yeah, a slider that I'm familiar with is a range in HTML, but anyways, I stick to what I'm used to here with the slider. So you can quite easily create a slider with JSServe. It returns you this new type, which has a field with the value, which is an observable. So you can connect it to other observables. And if you actually put it in any div or in any HTML DOM, it will render the slider. And then you can actually, like this, update these observables. And And I think this is pretty nice for writing UIs for visualizations, because you kind of separate the visualization, the plot, from the UI. Yeah, which is kind of cool, because someone might write this function simulation plot in a package for their simulation software. And then anyone can write a UI for it to explore it. Yeah, so here's a very simple first version where I use these JSServe widgets to actually update the simulation visualization. And I did a bit of a funny thing here, because as I told you, Makie also has these widgets like sliders. And the new thing is they also work now in WebGL Makie. So any GL Makie UI or dashboard you've written should also work now in WebGL Makie. It's a bit slower because it needs to do this round trip over Julia to JavaScript. So it's not as smooth, I would say, as it is in GL Makie. But this one is the one that actually is just like a plot. And this one is a HTML widget. So this here is just a canvas, basically, where Makie does all the drawing and plotting. And this also shows you that you can just insert a Makie figure that I created here anywhere in the DOM, and you can also put inside multiple figures inside an HTML document. That means if the Makie layouting isn't enough for you, you can also switch to HTML layouting pretty much. Obviously, I'm not very good at HTML layouting here. Or I actually wanted to keep it simple, because otherwise I would have tried to align this here. But yeah, this also shows you that you can update these plots from very different UI frameworks. That means if you're more familiar with GTK or Qt and already have things set up there to make these kind of UIs, you can use that as well to just update these kind of visualizations. Yeah, so, but that means there's a choice. Makie offers UI widgets, JServe offers UI widgets. So when should you use which? And what speaks for using the JServe widget is that HTML has been used for this for years and decades. So they're very mature, they're very customizable. It's very easy to make a super fancy slider or a very fancy layout and things like that. And you can, in JServe, you can use any JavaScript library or CSS library or HTML library inside your project. So you could just start using Google's Material UI or things like that. So the choice of what you can do is much, much larger. And obviously, if you want to actually have your dashboard end up on a website, you should go the web route. And yeah, you can put together with JServe fairly complex JavaScript interactions that will stay active on a web page that doesn't run a Julia process. As I said, like WebGL Makie is kind of driven by Julia. So if you kill Julia and have it on a web page, the interactivity will go away because it can't actually get the updates from Julia anymore. But yeah, you can actually also update the plots inside JavaScript directly and write JavaScript for it. But it's of course a bit more tedious. And why not? So WebGL Makie, as I said, is not as fast and feature complete as GL Makie. You must run it in a browser or Electron, which is not always desirable. You might just want to have a nice little desktop window, which is native. And yeah, there's no way around paying the cost of serializing your data. So if you have millions of particles you want to visualize at like 60 frames per second, you won't be able to do that in WebGL Makie. Yeah, so now I'm using the whole range of JServe widgets to actually complete this kind of input that the visualization has. So I have a slider for the time, I have a slider for the level. I can choose the field here. So we have kinetic energy, potential temperature, and so forth. And we can actually choose a projection. And now I also have a toggle to actually show the Earth overlay. Oops. And yeah, I have these sliders here. And I just want to say, so I said a lot that WebGL Makie is slow, but this is quite a bit of data here and it's pretty smooth. So I think it's definitely usable for quite a few use cases that you can think of. Yeah. But this is very basic here. This is how it has been the whole time with JServe. I now want to make things a bit easier to make it look fancy. I worked a bit on styling these widgets a bit more, and I wanted to show you a bit how this can work. So there's this JServe asset type that allows you to include any kind of other existing library for styling or for JavaScript. And one of my favorite libraries for easily styling your UIs and HTML is Tailwind. And JServe actually ships it, so you can just use it directly. It's just like, yeah, shipped within the repository. And if you insert it anywhere in the DOM, it will be loaded. And JServe also takes care that it doesn't get loaded multiple times. So if you actually depend on it in your own code, you can just insert it all the time to make sure that it gets loaded before you actually use the CSS classes from it, which I'm using here to style this a bit. Tailwind has very nice documentation, I think, which makes it very easy to quickly make like layouts and things like that. So where is it? Yeah, makes it very easy to do these kind of more complex layouts by just adding a few classes to your HTML. And that's what I did here. I think there are two basic ways of extending JServe. So if you want to write like a little style dashboard package in Julia, I would recommend two ways. One is just like writing functions that return HTML, these DOM fragments, basically. And then others can use these to style their application and make it a bit easier. So here I made a little more styled slider that allows you to have a title and actually see the value and make it look a bit nicer. And you see here, I need to now in this function return the slider and the HTML I actually want to display for the slider. Which is not always what you want. So there's a second way of doing this is by creating a new struct. So I called it here style slider. And I just have the slider in here. and the HTML that it should display in another field. And then I can overload JS render to actually display it, insert it into the DOM. And that's also how Makie, WebGL Makie inserts these figures into the DOM. So Makie just overloads JS render and emits the correct HTML to show the plot. But this way you can just have the style slider here, insert it into the DOM, or do something here with slider value whenever it updates. So these are kind of equivalent. The function one I use usually for prototyping, and then when I kind of want to offer it to other users, I get more serious by actually creating these structs and overloads here. I've written a little widget library like this here, which I want to add to JServe. So this is really at the edge of development, basically, because JServe is still not very highly advertised because the docs aren't that polished, and it doesn't have these easy ways to make styled dashboards. So I haven't been advertising it a lot, but I think I will do this in the next month and have a release with all these widgets in there, which make it very easy to create a bit nicer looking dashboards. And now if you put this into action, it looks a bit nicer. It's more readable. You have like titles for the different things. The layouting is a bit easier with these row and call list widgets I've added, which makes it very easy to align them and put them in there like this. So I think this is already a pretty basic and pretty simple dashboard you can do. And if you look at the code, it's not that much work to actually set this up. Yeah. Any questions so far for this widget dashboard part? Okay. Then I want to show you a bit how what you can do with this app. I kind of didn't really mention, like, why do we wrap this always into this app? It has several reasons. First one, it makes it easier for me to show it, display it in Jupyter, for example. But there's also another big reason for it. It's that you can serve it on a web page. And that means every user gets their own, everyone that goes on your website looking at this dashboard needs to get their own version, right? Because they play around with it. It needs to be global. And that's kind of the reason why it's wrapped here in this app thing, because that means this one should be an isolated unit, right? But that makes it very easy to just serve this to your users. So JServe just exports the server that you can hand in the app. And since I'm here on Docker with Jupyter Lab, it's not super straightforward to host it and visit it in the browser, because yeah, you kind of need to have this proxy URL here. And that's what I need to set manually here. I think this is a bit more of an advanced topic, but with this, it actually works to just serve this on an URL. And if you have your server set up correctly, this could be, yeah, anywhere on the web. And then you can show this to your users. You just need a server that has a running Julia installation, basically. And there are a couple of other ways to do this. So there's the static export that creates just static HTML files without a running Julia server. as I mentioned, that means you don't have all the Julia interactions anymore. And if we go here, we see what it exported. It exported 2 HTML files. Just to show off that you can have like these routes, I did a very, very simple app that just takes you to the other app here. And if I export it like this, with multiple routes, I actually need a static file server, which can be just like what GitHub does, for example, on GitHub Pages. So if you put this on this folder on GitHub Pages, it should just work. Locally, you can serve it with, for example, LiveServer, which just serves the files that are in the folder. So here you have this. But as I mentioned, all these sliders work in Julia, right? They load data in Julia and do the updates in Julia. So these are not working anymore here. What does work still is the camera, the 3D camera. So you can zoom around here in 3D. That's just because I already implemented that in JavaScript. If I have time, I want to do that with more primitives in WebGL Makie. So for example, that you can do the 2D zoom and that those kind of things stay interactive once you've exported it without a running Julia process. And there's also a prototype how to kind of cache what Julia would be doing. So you can record a state map for every state of the slider, get the values that Julia would produce, and then load them whenever you move the slider. So I made a third demo of how to export an app that runs everything in Julia, caches all the states, and then creates an HTML page that will still stay interactive after exporting it. And I think that's here. If it's a single HTML, I don't actually need the file server. I can just directly open the HTML. I can share it in an email. I can, put it on GitHub or wherever and should just work. This is taken from the docs. This example from the WebGL Makie docs. So you can see the 3D camera is interactive. And all these state updates here are cached. So this stays interactive. And this way you can make very simple plots stay interactive even after this kind of static export. But yeah, it's a bit experimental. As you can imagine, if you have a lot of sliders and a lot of states, the combinatorial explosion happens and you will generate gigabytes of data, which will maybe crash your browser or just will take a long time to load. There are a few ways to help with this. I'm not sure how much time I will spend on making this route better, or if I will just move more and more things to JavaScript in the end. Any questions for this? Yeah.
In which format do you save the data for the plots?
That's WebGL Makie's own format, pretty much. What I do is basically just create dictionaries of the Makie plot objects and convert a few data types that are not describable in JavaScript, and then send them to WebGL Makie.
I was just wondering if you can save it in binary format to make it more efficient.
Yeah, it's already saved in binary. So I've actually put a lot of time into making this this communication with Julia as fast as possible. So this uses the connection with JavaScript uses message pack and compression to make the updates as small as possible and as fast as possible. So I think, yeah, as you can see, this is quite a bit of data and it's pretty smooth. I think Lazaro wanted to show one example that's a bit slower, like when you have a so Makie has several 3D axes, and one of it calculates everything in Julia to figure out where to place the labels and everything, and what to display in the axis. And this gets surprisingly slow because it needs to do so many things in Julia and then send a lot of updates to JavaScript. So, yeah.
I have another question, if I may ask.
Sure.
So you're mentioning converting some Julia function to JavaScript to make it exportable. So what is your idea about WASM, where you have like C and Rust can compile down to WASM? There has been a fork of Julia of 1.3, I think, which was also able to use WASM, but not.
Yeah.
So is this the future, do you think? Or is it really
Yeah, so
long
compiling
time?
Julia through WebAssembly would nicely solve this issue. Then we could just compile everything to JavaScript and everything would just stay interactive and would just work. But I think we are quite a few years away from this. There are a lot of little problems that need to be solved and there's nobody working full-time on it. And I think even if we now had someone working full-time on it, it would take quite a while to make it usable. I wondered if we could have like little functions that just get transpiled to JavaScript so that you can make a few things a bit easier. For example, we have this data inspector in Makie to get like hovers over your data. And a lot of times you kind of want to transform the data that gets displayed before you actually show it to the user. And this one would be a small Julia function that gets transpiled then to JavaScript and stays working pretty much. But I think, yeah, that will already push it because it's kind of complicated. So I think right now I'm trying to make the other ways smooth because I don't know, it's probably 5 years away or 4 years away to compile Julia to JavaScript. And then it will be a different game. But until then, I think we need a good solution to do these kind of things.
Work into this JS serve, and it's very good news. It looks really powerful, and interacting directly with the DOM is, I think, a fantastic idea. So where do you see this going? You also mentioned that you're going to put more work on these next months or so. Where do you see this going?
That's a good question. Yeah, I mean, I guess it should go into the direction of Shiny or things like that. And I really want to prioritize that people very easily inside Julia can show their data and share interactive ways to show their data on the web or wherever. I don't want to say it should become the standard way of doing it. It definitely will become the standard way of doing it in Makie, I would say. Although we are working, JServe is very flexible in the way it communicates with the front end and the way you can actually insert it into other apps. You can just export fragments of your application and put it somewhere else. So JServe should also be able to integrate into Genie and yeah, or other apps that come up in Julia. So yeah, I try to make it as flexible as possible so that it has a nice road to the future for Makie being able to be displayed anywhere.
Yeah, basically in any HTML.
Yeah.
Irrespective of what other frameworks are running behind.
Yeah.
Yeah. Awesome. Thank you.
Cool. Thanks. Yeah.
I just have a question regarding the loading of data when you're plotting it, especially when just now when we're seeing that we loaded the time series data, you've loaded like 10 different days at the same time, and then in the serve, when you're doing the JServe, you're just using the JServe to select which part of the array it's being plotted.
Mm-hmm.
Is it necessary to load all the data at one shot, or is it possible that you could basically, because especially for climate data, if the climate data is very big, you may not have enough memory to load all the data at one shot. So is it necessary to load all the data, or can you just load a certain time series using and then use live, and then with do you have basically my question is, do you have to load all the data at one shot, or is it possible in some way to load one part of the data at one shot, one part of the data?
I don't think that's Makie specific. I think you should just be able to use a memory mapped array or like a lazy array type. I think there are quite a few that got presented here. And if you switch that out, you won't need to load the whole data. So that's just because it was easy for me. I'm not that familiar with all these lazy arrays that make it possible to work with data that is larger than the RAM. But yeah, I think the Julia offers a lot of tools there, and you can just use them with Makie, of course.
Okay, thank you.
Thank you for the presentation. It was very, very interesting. You mentioned you had to solve the transport of data from Julia to the browser, to the JavaScript runtime. So can you talk a bit further on how you solved that, and what different methods did you find? I remember like there are the binary transport protocols like gRPC or tRPC. Have you looked at those? Thank you.
I haven't looked at those. It's actually, I think, the first time I heard of them, but I looked at the at all the popular JavaScript binary protocols, and there weren't that many that were mature and fast. So I ended up with MessagePack, which in all benchmarks seemed to be the fastest. And that's kind of how I got stuck with it. There are a few, it should be relatively easy to swap out. So I think when there's something else that seems promising, it should be just a couple of days work to actually swap it out. And then I will do it if it's worth it. Yeah, that's cool. I will.
So I was wondering about the source of data that you're using. From kind of eyeballing it, it looks a bit like a kind of a coarse resolution model output. I was wondering what the resolution is, and maybe you can say something about the models that was used.
I actually can't. It's from the climate machine, and I have no idea about the model, to be honest. They just gave me this time series to make a visualization for it, pretty much. And I didn't dive into how it got produced. But it's open source, so this example. It's part now of the Cremer Makie core package as an example. And maybe you can look there for further information.
Do you know like the size of the arrays, for example, by and large? wondering if it's 100 by 100 or if it's like a million by a million. You know?
No, it should be something in the thousands, I think. Oh geez, it wasn't that easy. So actually yeah, I don't know. Maybe we should just.
Okay. No, it's okay. Thank you.
I don't think Klima's climate model, I don't think they run it at super high resolution. So it's probably 512 by 256 at the max at this point. Yeah. That's based on what I know.
Yeah. I can send this around later. Yeah. Yeah, that's a good question. I mean, that should make put the performance into perspective. Yes. Yeah. I guess it's timeout, although Lazaro might not use all the time, but maybe then we can move it after he's done. Any more questions? Okay.
Okay, so as I referred before, we are now having a hands-on session on visualization of Earth observation data with Lázaro Alonso. Stage is yours.
Should I connect this?
Yes.
No, I have
okay.
it, but I need some water. Should I leave the water? Yeah, no, I have it. Doesn't work. Hi. I think it's displays. Range. Yeah. Apologies for the delay. It doesn't work. Probably I need another one. You have another one? To use another convergence. Tens algum professor de aquele que se usou ontem? Onde é que está o que se usou ontem? Aquele que se usou ontem. I mean, I can see that the text thing here, but yeah, it recognizes something. Yeah. Tries to connect, but that says that doesn't work. Not today. Not today. Yeah. Flickering. Este eu estava a fazer o flicker. It's okay. Really? Really? I think it's okay. O adaptador que achou mesmo que estava ontem.
É este.
Esse adaptador.
É o teu.
Okay, while we fix this, I wanted to ask who has Julia installing their computer? Okay. So it would be okay for you guys if you go to the repo and clone it and just work in your computer locally. Because I mean, in my computer, the Docker image didn't work, so I will not be using Docker at all. I mean, but you could use it as well, and it should work there also. But I would like to actually do the coding live, so that you can actually follow line by line and see how things are done, at least for my simple examples. Okay, it's not that complicated, but still, I need to say aloud. Right? Is it my computer or is the?
No, the Max. It doesn't like.
It doesn't like the Max.
Max
Okay.
ones.
So, can I borrow someone else's computer? A Linux one? I don't know.
Try this one. Try this one, but probably that one.
Eu acho que estes
Because I also have mine here. Yeah.
offset computadores.
No signal. Yeah. Doesn't work. Let me try again. Yeah, it used to work. I mean, I use all the time. I use this all the time at home. No.
This one is equal, but it's. I think the problem is with the Max, really.
Yeah.
This connection, disconnected. Do we have a plan B?
I mean, I just need a computer. Yeah. Let's see how long we have. Okay. Yes. So today, yeah. Better? Even better, yeah. So thank you for having me. So today I will talk mainly about data cubes and how to visualize them with Makie. But before going into the topic, I just wanted to show you this project that I have been doing with Makie, where you have different climate visualizations. So you can actually go here to this webpage, which is on GitHub, and click on some of them. And here you have live examples that actually just work here. Okay. So this is the thing that Simon was talking about before. So you can actually customize the whole thing pretty well if you know a little bit of JavaScript, HTML, and Makie all together. So yeah, just wanted to show you the things that you can do. Yeah, small detour, which is okay. As for this workshop, the material is in JuliaEO, in this subfolder, but if you don't want to clone the whole thing, it's also here in my account, so that if you want to work locally, you can also do it with this folder, or you can do it in the Docker image. It's supposed to work on all Linux machines, so all the steps that I'm doing here, they should work, okay? And if they don't, then we talk about it afterwards, and we try to fix it for your specific case. So the topic, data cubes. So this data cubes is part of a bigger project that we have at the Institute, which is called DeepCube. And DeepCube is a research project that aims to explore and develop new deep learning approaches to address relevant Earth system dynamics. So basically, we are looking at droughts, heat waves, and migration flows, if any there. And the goal here is to collect a lot of data with high resolution. These cubes here are 30 meters. So each pixel will represent 30 meters. And apologies by the figure, but we sample a lot of them, like 50,000 of them, all across Africa. Because this is the use case for this project. So this is the thing that we have. And this work has been recently presented in New York IPS 2022, so just last year. And yeah, if you want to know more about it, you can go and look for this learning to forecast vegetation greenness at fine resolution over Africa. And it's also in archive, and you can see how this is actually used there. As for the coding part, which is the thing that we are doing today, it's just grabbing the data and doing some heat maps and some cubes, which are like these ones here. So if you have the folder with the manifest and the project, you can instantiate that, and things should just work in iJulia. So I will be using all these packages, not really, just from here to here. The first two I will not use, but we could use them if it's needed. So in the normal workflow in the Jupyter notebook now will be to call WebGL Makie, activate that backend. Usually you should have this line, because usually you will have the different backends while you are doing your data analysis. At least that's how I do it. I mean, I have ChairoMakie, GeoMakie all together, and sometimes I switch between them just to have like quality, the picture that I need for my publication, or do I need the interactive one to do the exploratory analysis? As for data, I usually have JAX arrays and the netcdf package plus dates. And I use these packages to open netcdf files as dataset cubes, I call it. We call it like that, where you have like longitude, latitude, and time, and you will have different variables within this dataset. In this case, because the target for this project was to investigate the greenness, we calculate a vegetation index called NDVI. The details doesn't matter, but yeah, it's called NDVI. And in this case, because we were trying to do some predictions with some LSTMs, you will have your target and your prediction. So within this data set, we encapsulate all these variables. You can see here you have your target, and then you have your predictions. And I just display here the content of each one of them. I must say that this information here is lazy, so you don't have the data actually in memory, so you can just grab the things that you need before you plot. Just as a simple case, I just go for the longitude, latitude, and time, because I will use these variables later on. And as a simple example, I start with a heat map, which is the simplest thing to do with this kind of data set. So for this heat map, first you define, okay, there are different ways to do it, but the way I did it here, I just did like a color map, a global color map that I will use everywhere, and a global color range that I will use everywhere in this notebook. So I put it at the top. And the names here, color map and color range, are keyword arguments in the Makie functions. So when you pass this to the Makie functions, it's enough to just say color map and color range, okay? And that's why I did it. So in this case, you start with your figure, okay? You define your figure, you define some resolution. And then in this case, I say, okay, I will need 2 axes because I want to plot target and prediction. So I define my 2 axes, like 2 columns. So I do a for loop, easy. I put some labels for the longitude and the latitude. And then I simply say heat map in my first axis, the target for time 1. Use the color map that I define at the top, use the color range that I define at the top. Then the second step, I do the same for predictions, and that's basically it. If you want some extra changes to your plot, as this hide decorations function is pretty useful, so that you hide the decorations for the second plot. So that's the workflow that I usually do. Or most people should do. Like, if you are having the same y-axis, you should not show the ticks as well, right? Okay, in this case, the labels. And when you pass this keyword argument here, tick equals false, just means that you should keep the tick here in the second plot. If you don't pass this one, this should go, and this is dangerous now because it's live coding. So you don't see the ticks anymore, right? And this last one, which is call gap, will take your full layout and reduce the column gap, the gap between the columns, to 0, so you don't see any gap there, right? If you change this, then I'm supposed to have, yeah, space between them, okay? Then you can pass, again, your ticks equals false, so that you can keep the ticks. You can do the same for labels as well, and other arguments. What did I did now? Yeah, it's in high decoration. Sorry. Yeah, it's here, right? Thank you. So the pretty cool with this now, with this backend that I'm pretty excited, is that you can actually do a zoom in here in the heat map, and you can see all the details that you want to. This was not possible before, I think, some months ago. I was not able to do it, but now you can do it. Now we have an error that is good that happens now, because now Simon knows that there is an error here. I zoomed too far, right? So you should have like a callback, like stop. And now, because this data set contains 10 time steps, the next step could be like, I want to plot all the 10 time steps as heat maps. So the next step that I did was to define this layout where I plot all the heat maps with this arrangement. And it's pretty the same workflow as before. I define my figure, I define my array of axes in this line here. So you have your array of axes in this line here. And then you just say, do me a heat map in each of one of these rows, right? I mean, for row one, do me 10 time steps. So do me 10 heat maps. Then for the second row, do the same, which are the predictions. Then I do the same as before. I hide the decorations. Now for column 2 until the end, so that you hide all the Y decorations. And then you say, for the X decorations, hide all the ones for row number 1. Okay, so that's the thing that you can see here at the bottom. You don't have any decorations for the Y-axis from column 2, and you don't have any X decorations for row number 1. What else? Yeah, there are several options where you can change the Y label, the X label, and you can even put a title based on the time. And we cannot see here the far right, so that's why I changed the number here to have a smaller image. So now I run it. Let's hope that it works. And we wait. So by the way, doing this in the new Julia version in 1.9 beta is pretty fast. So I don't need to wait any time, but now I need to wait. Why do I need to wait so much, Simon? Is this actually what? I mean, for each, yeah, for each heat map is only 128 pixels. It's not that big, but now it's been super slow, which I don't know why is happening. Yeah, the Docker didn't work at all with me, and was pretty slow. It's not running. This one here, right? It died. Oh no. Maybe I just need to kill it, right? Yeah, I don't know what's happening here. Okay, I'm not afraid to kill things. So I will kill the kernel and I will kill the whole session and I will start again in a minute, okay? Just see if it works. And if it doesn't work, then we try again another day. So if you have this in your computer locally, it should be working.
Something?
Yeah.
I forgot a few things.
A few things, yeah.
Okay, I'll use this time to show something that I forgot.
Yeah.
Okay.
Yeah, so I tried to run the hands-on notebook that you made, and it worked great in the browser, but it did not work for me in Visual Code with the sliders.
Ah, yeah,
Is
that's
that
not
like
expected
a
to work
issue,
yet.
or is that something that's?
So every platform has their quirks or IDE. So Jupyter, Pluto, VS Code. It cost me a lot of time to get them all working, and VS Code I haven't done yet.
Okay, okay, that makes sense.
Yeah, I just wanted to quickly show two things. So first of all, this exactly same code that I included in the notebook
works pretty seamlessly also with GeoMarkie and looks kind of the same. And I actually started out with having this as a GeoMarkie UI. So with the Markie native widgets, basically. Oh, it needed a bit to compile, I think. So yeah, you can swap these out pretty interchangeably. That's something I just wanted to quickly show. And another thing that I actually saw today is that it's a pretty historical day for Markie. Because we actually are just about to become the most starred plotting library in Julia. We took over plots.jl half a year ago or something like that in May. And now we're going for Getfly, and I think there's just 1 star less than Getfly. So if anyone wants to make the star, then we can overtake Getfly. Cool. Awesome. Yeah. So Getfly is one of the oldest Julia plotting libraries. I don't think it's actually used that much anymore, but since it had such a, you can see like time just helps with stars. They just go up usually. But yeah.
That was it?
Yeah.
Good. I will try to change to okay. Yeah, it's not interactive.
Okay.
Good. So I will continue with the functions. Unfortunately, they will be done with the other backend. So yeah, I will go back to GeoMarkie. So I will use GeoMarkie now, which is also interactive. Okay. So, I mean, this is the beauty about Makie also, that if one of the more experimental backends doesn't work for you, then you just go back to the ones that you know that work all the time. Now it's taking too much to load. Yeah, we're good. So I will rerun things and we will see the output, because I actually want to show you the cubes. So that's the whole goal of this, right? So now we run this one. I already explained the code, and let's wait for the first plot. So just in case it doesn't display figure. Okay, while we wait for the first plot, takes a while. Oh, it's okay here. So if I call display, as Simon mentioned, I should get a screen with the plot. This is always an issue when you do the live coding, right? If you just prepare the whole thing and you don't run anything, looks awesome, right? Yeah, I don't know why I don't see this here. Okay, never mind. So the other way of plotting this data could be like an unnecessary 3D plot, right? I mean, you don't need it. But, I mean, I could do all this heat map as a 3D plot as well. So in order to do that, I define a grid of points with these dimensions, okay, which are the dimensions of my heat map. And because I want to use a rectangle as a marker, I mean, to actually have each one of these points with a value, I define this marker here, which it just takes as coordinates my point of origin and the size of this marker. And because I need the values from my my array, I reshape the whole thing to a one vector of values, because that's the thing that I need to pass. So if you run this line here, you will have a full vector of points. And here you will have a full vector of values. So when you do that, you run that, and then in order to do up a 3D plot, you use this axis LS scene, where you pass your figure position, and then you just simply call mesh scatter to your axis, the points, the marker. And now the marker size, it's important that in marker size, you pass all the values for each one of the points, so that you can actually see also the effect of the actual value for each one of them. And the other keyword argument is a color. So you need a different color for a different value. The color map that I defined already at the top, and the color range. Then you run this, and you should be able to see a new plot here. So which is a 3D plot that does, I mean, necessarily is useful, but you can do it. I will try again to do this display figure. I think now it works. So you can actually have this interactive window here and do the zoom in, right? And explore your valleys in your data. I mean, you actually don't need it, but yeah, you can use it. The other axis that I really like is this called axis 3, where you can plot exactly the same data, but it has some more keyword arguments that allow you to have like the labels and a title, and yeah, like the elevation, perspectiveness of the plot. And it's pretty pretty handy to have this axis 3. So you have it here. You can also explore your data as a 3D object. Okay. So, and you see it's pretty simple data. It's just a heat map. So the only trick here was to generate the points, to pass the marker, and to pass the values. That was it. Something that I really like here is that you can use this axis and pass 2D functions as the heat map, this one here. So if I run this one, this function here, I have my axis, and then you can see here that I'm saying in this axis, plot the heat map of this array. And the default is to put the heat map in the X, Y axis, okay, at 0. And this suggests that you can use heat maps in 3D, right? And that you can position them in different places. So if you go to the interactive window, you can see where this heat map is located at. So regarding transformations, then you have this keyword argument here, which is called transformation. So you play with this one, you will see where this heat map will be located now. So this is a transformation in the Y set axis, and this second argument is the location. So the location is at 0. So you put it here, okay? And this is for the first time step, and you can do a simple for loop and put several of them, right, in different locations. So in this, So in this case, it's at 0. So the next step that I did, I was like, okay, I have 10 time steps, and I will just simply pass my index for the time and the position from 0 to 1 in this range. And if you do that, then you get all the slices of the heat map over this axis cube, I will call it now. So if you want to go to the interactive version, you see display, and then you have this display here of your heat map. Okay, it's pretty cool. I like it. And as you can see, this was the heat map over each pixel, right? But then, just for the fun of it, you can also do this with scatters, specifically with the mesh scatter. So you can take each one of the pixels and associate a single scatter for each one of them, and do also a 3D plot of the whole thing. So as before, you define your points for the 3D space in time and X, and in this case in Z, because you want the points to be arranged in this fashion, right? And then the marker, you define a marker for this. Notice these values for the marker. I usually use minus 0.5 to 1, such that the marker is centered at the value 0 in this case, right? So the center for this one will be 0. So it's at the center of the value that I want to plot. And since I already have the values for my array, no, I do the values here below. Yeah, so you use the same function, the same call function, and the only thing that changed now is the points that you're plotting and the values associated with each point, which in this case I'm passing as the color. Okay. Then you run it, and then you get this. Let me show the display. And then in the display, you will get this kind of cube, which is made of individual mesh scatters, rectangles in this case, right? So you can see here, I don't know if you can see it, but you can see how they change from one to the other, right? And you actually can change the marker size so that you can actually see this effect. 0.8, let's say. Then I will just display here. I don't want to type it twice. Display. And here you can see that they are actually individual boxes. Okay. Yeah, that's it basically. And Makie has, yes.
Thank you. Yeah, this is awesome. I was wondering whether you were considering, well, you had considered sort of just plotting the sides as heat maps, like 6 heat maps, and sort of just adjusting them sort of dynamically, as opposed to plotting the 3D space of scatters. You know what
No, I don't understand what you're saying. Come again, please.
I was wondering whether we could do something like this with heat maps by plotting 6 heat maps on the side of the cube instead of a whole set of three-dimensional points.
Yeah.
Whether you considered that option or if it was just like...
No, I mean, I actually also do that. So in some cases when the data is really high resolution, where you have a lot of points. So, and you only care about the faces, right? So in that case, I just subset that data, and I create the heat maps for each one of the sizes.
Okay, thank you.
Actually, there is a tutorial here in Beautiful Makie. Sorry for the shameless advertisement, but so there's a tutorial on how to cube in Beautiful Makie, where you actually put images in each one of the faces. So each one of these images could be a heat map as well. Yeah, that also works. Yeah.
If you have, I have some cases for plotting like this where a lot of the data is missing. So you should be able to see through to some of the cells in the middle. Is it possible to do this with having opacity on the cells for some that are missing? Or?
You could pass. I think you could pass the non-color keyword, right, Simon, to the call function, so that if the color argument here contains non-values, missing values,
yeah,
then you do non-color equals red or blue, and then you will see the missing values there, or transparent.
Yeah, of course, transparency works better than
Actually, I have an example at the end where I use missing values, if I have time. Yeah. So let's see what does this one does. So Makie also contains this nice function which is called volume, where you don't need to do all these shenanigans about the mesh cutter thing. You just call volume over your 3D data, and you can get this volumetric plot for all your values as well. The only thing that I don't like about this one is that it's hard to see through it. But like they are too over exposed, like the colors here. You do this, I see a lot of red, and then I don't see a lot of details. And sometimes I actually like to explore pixel by pixel. So if I do the 3D one, which is the previous one, I can actually go below for my scatters, right? And actually explore each one of them and see where the values are or how they are actually. So, I mean, it's a matter of use case, right? So if you want to actually see each one of the values, then you do it like this. Or at least that's how I would do it. And I don't know, this one, display. I need to add display now everywhere. And the other function that is that I like more instead of volume is this pretty convenient function which is called contour. So in contour, it works pretty well compared to volume, at least for me, and it looks pretty similar to the mesh cutter output, with the main difference that you can see that the values are interpolated between them, right? So I don't see the discreteness of my mesh cutters. So this one is the one that we usually use. Let me see the paper. Is that the one that we use here? Yeah, I think we use mesh contour here. Yeah, looks like contour. Yeah, not sure, but yeah, that's the one that I use. And yeah, this is basically it. So you could do the heat map, you could do the mesh cutter, then you could do the heat maps transformation also to get the cube, or you could use volume or contour. Okay, so depending on your use case, you should choose. The last example that I have is a little larger data set. Let me see. Ah, no, this is still. Let me run it. Display current figure, I suppose. Do I have the data already? Okay, no, I think this is too. Yeah. This is just another example. This is for a test. Data set. And Makie contains a lot of predefined themes, so you can just pass with theme black, theme ggplot, theme minimal, theme dark, theme black, and your whole plot will be theme with that theme. And yeah, this is I remember what I did this plot. For the first data set, you only have 10 time steps, right? So you actually can do just each one of the heat maps, and that's it. So you are done with your figure. You can put that into your publication. But if you have more slices in time, like 100, 1,000, then this becomes like really nice to explore. I mean, I can see all the slices here and see and have an overall view of the whole thing. So yeah, you can use the heat map with the transformation, the contour, or the volume, and you can explore that. And as my last example, I prepared this SAR file, which is also in the repo. If you instantiate your project and have everything there, you should be able to use JAX arrays and SAR. Speaking of SAR, I will take a small detour again. So if you go to JAX arrays, this is the package that I'm using to load the data. And then in JAX arrays, there is an example where you can open files of several gigabytes, right? And just load the data that you need to plot in demand, okay? This one is also using Makie, so yeah. So I just wanted to mention that you can work with big data sets with these two packages. And when you load the cube, you are actually not loading the data, everything's lazy, and yeah, it should just work. And in this case, yeah, I'm loading my data. This case is pretty small, but this could be gigabytes. Yeah, whatever. And to do the heat map, I think it's display. I want to see the interactive one. Okay, I don't need it in this case because I just wanted to show that there is some data there. And the thing that was mentioned before, if you have a missing value, which in this case is encoded as a NaN value, we have this keyword argument, which is called NaN color. So if you want to actually see the amount of missing values that you have, you can put a color on them. So this last example is just to show this effect of having missing values. So if you go to your window, so you will have your slices, and where you have missing values, you will put a color. In this case, I put like a light blue color. So all these regions here are missing values, and as you rotate, you can see through the thing and actually do the exploration of your data set. So in order for this one to work like it's working now, you need to pass also transparency. So you put transparency here equals false. Then all the heat maps will be solid, so you will not see through them. And yeah, it will look like this. I mean, you will still see the missing values if you go to the other side with the camera, but in the front, you don't see them, right? So So you need to play a little bit with the keyword arguments and yeah, to get the effect that you want. So I usually, if I have transparencies and I want to show something that I can see through, I put always transparency and things just work like this. Everything should be, yes?
I have a small question. Does it also work with missing? So the missing literal in Julia, or does it just work with none? The feature with that becomes transparent.
Correct me if I'm wrong, Simon, but for this one, I think only works with none.
Okay. Okay.
Yeah. Yeah, that's what I do nonce, basically. So, and that's it. I mean, if you have any questions or you are trying to work this out in your computer and it's not working, or you have some use case, just let me know and we can take a look at it. Okay. Thank you very much. And yeah, that's it. More questions? Oh, okay.
A raster data, and you had the elevation of it? How did you get elevation of raster to create a 3D?
What visualization are you talking about?
At the beginning.
At the beginning?
Yes, you had a.
This one?
Yes.
No, this one is just the heat map
okay.
data.
Okay.
So actually, you will have topography data as as the elevation data, and you can just pass this array of points and your values for your elevation data and call this function, and you will get this nice topographical plot.
Okay. Okay. Thank you.
Yeah. I think I did that one.
But I guess you could do that with any matrix whereby the value would be extruded, right?
It depends where you put your origin. So in this case, I put my origin at 0 so that all the markers start at 0. But you can also do it
Negative.
Negative, yes.
Yeah, sure.
Actually, I have an example for that somewhere, but okay, sorry, but this is, I post most of my things on Twitter, so so that I can show off a Makie to everyone. Okay, this is not working out, but I have something that works both ways, and it's for temperature, and yeah, you can see how it changes over time. All right, that's it. Thank you.
Thank you.
I don't know. Is this one yours or mine? Probably this is mine. I don't know anymore.
Okay, time for lunch break. So until 1. Be here at 1 for us to then start with the parallel sessions. Okay. Thank you. Have a nice lunch. Okay, is everyone ready for this second part of our second day? We'll have very interesting sessions on this afternoon. And now we'll have two parallel sessions. The parallel session 2.1 with the title of The Power of JuliaGeo by Martin Visser. It's going to take place here, while the parallel session 2.2 start processing background and method with Simon Lupemba and Lippert. Eigen Lippert, sorry, will take place in another room where I will take you to there. So for the people who are going to stay here, I'm going to present Martin Visser. Martin Visser is a hydrologist at Deltage, where he focuses on integrated water resources management, as well as building open source software to support it. As an early adopter of the Julia programming language, he's been active in the open source community, helping to set up and maintain JuliaGeo and its packages, which aim to make it easier to work with geospatial data in Julia. Thank you, Martin. Persons who are going with me to start processing, you can follow me. Thank you. Mario, grazie. Vai seguire con YouTube. This is surprise.
Okay, welcome everyone. So I'm going to talk about the power of JuliaGeo. So this is a plenary session. I am going to show some code and some slides. With the code, I'd say mainly let's just focus on what I'm doing and following. So you don't need to run it locally at the same time. But if you want to follow along locally, in the GitHub repository, all the materials are there. Yes. So let's start with a few slides. So this talk was titled "The Power of JuliaGeo." So I had to think a bit like what is the power of JuliaGeo, if any. So one analogy that I could come up with was thinking about Lego bricks. So there are a lot of Julia packages related to JuliaGeo, and they all do something useful and often generic. But when you really want to build a workflow or do science, then you need to combine them together. So this is something that JuliaGeo and its packages and the Geo interface tries to enable and tries to make easier to stitch this all together. So that's what I'll be focusing on. So first, a little bit about me. I'm a hydrologist at the Deltares Research Institute in the Netherlands. So I started using Julia at Deltares in 2014, originally doing more point cloud processing. So there's a picture there on the bottom. So one reason back then for me to use Julia is because I knew I wanted to do custom kind of processing. So I needed to just be able to loop over all the points in the point cloud, and it needed to be fast. And for instance, what you see here is a two-dimensional array of colors. Like that's what an image is in Julia. So it was very easy for me to write some code that just maps every point to a pixel and do some visualizations, for instance. So back then already it was clear, like there were infrastructure tools and input and output packages necessary, for instance, to read point clouds and to write rasters. So that's what originally got me to help with contributing to packages. So I should say that now I'm more focusing on the simulation software. So I helped to write a WFlow, which is distributed hydrological model. And currently we are working on more water resources model that is built on top of modeling toolkit. So what is JuliaGeo? One obvious answer is that it's a GitHub organization, but I think what's more important is that it's a community of people that are using Julia and are working in the geospatial domain. And a lot of them, they have certain needs to make their work easier, to build shared infrastructure. So basically since 2014, I think I just went back into the archives actually a little bit, looking at the old, like this is Fabian Gans back in 2014 suggesting, hey, let's set up a mailing list together so that we can discuss what we should build. And that's had been done. And then a year later, we had a bunch of packages that were useful for geospatial data processing or input output. And we decided that it's good to set up JuliaGeo and to move some packages into there and then try coordinating a little bit better. There's this website, JuliaGeo.org. It could use more work, but one of the useful things there is that we try to list packages that are useful for geospatial workflows. So not all of them are inside of the GitHub organization. Some are inside, some are outside, but that doesn't really matter in the end. Putting things inside a GitHub organization can be useful to, if you want to do maintenance together, or things like that. So this is the GitHub organization. So right now there are 25 repositories in there. Some actively developed, some are already archived. And I should mention, like on this course, there's under domains, there's a geo category that you can use to reach out to the community, as well as on Slack. I list here a few other GitHub organizations that have similar goals, and the goal of JuliaGeo is not to be on an island, but to be well integrated with the rest of the Julia packages that are out there. So for instance, Julia Images, it was set up by people that were doing microscopy, and so on the tiniest scale, but the code is generic and it works just as well on the larger scale, which is Earth observation data. Yeah, that's why I list the other packages here, or ecosystems here. So one of the things that early on the JuliaGeo community basically agreed on is that it would be very useful to have wrapper packages available for the existing OSGeo open source packages. Also, if you look at the R and Python, a lot of this software, it relies on these C++ packages. And so there are multiple ones, like Proj is used for projections and coordinate reference systems. Geos is to do operations on geometries like polygon intersections or line distances. And GDAL actually makes use of both of that and adds input and output for many different file formats, both raster and vector data. But JuliaGeo is not limited to this because while it's very useful to have these packages available, sometimes there also can be advantages to having things in pure Julia code, for instance. So we have both in JuliaGeo. So directly to skip to like what could be improved in JuliaGeo. I should mention that one of the reasons that I'm excited to be here is that I think for a lot of the JuliaGeo folks that it's the first time they really meet each other in person. So already after just one day, at least I am like full of new ideas and inspiration. And we discussed, for instance, that maybe it's time that we actually made a roadmap and start writing down some of these ideas. And as I mentioned right at the beginning already, something that could be improved and could make it a bit more accessible, I think, to a lot of people is to work on cross-package workflow documentation. So to go back to the Lego bricks, like how do you combine them to build something cool like Penguin? So that's actually what I'm going to focus on in my demo. I'm just going to do some geospatial data analysis, I guess, as a way to show you how you encounter different packages, how you can use them together, using, for instance, the geo interface package. So I'll switch to that next. So is this readable? Shall I make it a bit bigger? Is this okay? A bit bigger. Good. All right. So in the GitHub repository of JuliaEO, I uploaded a notebook, but I personally prefer to work just in Visual Studio Code interactively, and because you can also see the output directly. So I'll be doing that, but the script is the same. Yeah, so I'm going to start off with the first package, which is package that makes a certain data set of the global administrative regions available. What I'm going to do is to load the polygons of 2 different municipalities in the Azores. And those happen to be the only 2 in Terceira. right? And so what we get back from this is an ArcGDO geometry type. So this package is actually using GDO to load this data set. But next up, I'm going to load the geo interface, and I can use this function, which then, it's easy to remember, and it's stable across packages, whether it's an ArcGDO polygon or a different polygon. But we can do a union and we get a single polygon out. So yeah, to be able to see what we are doing, it's very helpful to actually do some plotting. So I'm going to use Makie in this case, because I'm working locally and I have a GPU available. I prefer to use GeoMakie. So what this code here does is there's a package called GeoInterface Makie, and it enables it enables to plot these geometries that we have available. So all that we need to do is to enable, to call this macro to enable it on the geometry type, on the abstract geometry type, such that we can dispatch properly to it. So I just ran the first two municipalities. It's not displaying now. Right, so this is the island where we are, and so this is a polygon that's now plotted in GeoMakie. If you zoom in here, you can see how detailed this polygon really is. I think it's around 15,000 different coordinates. So you can zoom in and out, and that's the interactivity that GeoMakie offers. Yeah, so we could also just show a single municipality, for instance, or add the second one to it in a different color. So another thing that's part of the geo interface is to find the bounding box of geometries. So in this case, it shows you the coordinates of the island, the bounding box of the island. So that will be useful next, because we're going to use a package that is newly registered now, since today actually, that Alexander Barth has been working on. So this implements the spatial temporal asset catalog, and it is something that is used, for instance, by the Microsoft Planetary computer to make it easy to programmatically access the data in the cloud in this case. So what we're doing here is we are creating a catalog object from a URL. So this is basically a JSON document that implements the stack specification. And so this catalog, we can query it. So there are different data sets available in there. Actually, so if we go to the Planetary computer website, for instance, you can look at their data catalog, and you see there are lots of different data sets available. So some are features, some are Earth observation or model results. So actually I didn't actually know that this was already in here, but this is from my institute. So this is model results actually based on the Wflow model. That's a Julia model. So that's nice that that's also in there. So we have the catalog, and the sub-catalog that we're going to look at is the Sentinel-2 imagery. So we're going to do a search. So this is a function provided by Stack, and it's going to look at the bounding box of the Terceira island for this period. So that is last summer, basically. And it's going to collect all the items. And here you can see there are actually 122 different scenes available from Sentinel-2. So let's pick another random one. It's hard to actually find one that's cloud-free enough. You have a lot of clouds here. So what do we get then? We get an item, and this item has an ID, which you can see at the top. It has its own bounding box, and it has a list of different assets. So these are the different bands, and they can be at different resolutions. And there's a metadata in there. You can look at a small thumbnail, like a render preview. Yeah. But so this geometry that's in there, it shows actually the outline of the image, and that's actually useful to show a little bit about the geo interface again, because this is a different package. It's not the ArchGDOL geometry, but it's a native JuliaGeo JSON polygon. But that also implements the geo interface. So for instance, if we want to convert that to well-known geometry, so well-known text in this case, that is very easy to do. So here you can see a different representation of the same data, whether it's text or binary in this case, in this binary format. So if we want to plot this again, we do have to enable the geo interface Makie on this type of geometry, and then we can do a plot. So I'm plotting here two things. So I'm plotting the extent of the image that we have, but I also want to know, hopefully Terceira is inside that image. That's what I want to check. So I'm plotting the island inside. So let's have a look. And indeed, we can see that it falls inside. I decided to plot it in green because it's a very green island. So I showed you before all the different layers and the bands that are inside. So let's just pick one. I'm going for the blue one because then I want to be able to see the difference between the blue sea and the land bit. So to get this data, so you for none of this you need an account with Microsoft, but to get the actual data, so for the metadata you don't need to authenticate or anything, but to get the actual data they want you to create a token, and this is a token that basically the way it works is this asset has a certain URL available. So this, in the end, it's just a .tiff, but we have to generate this token for this catalog, and that looks like this. So there are two things in here. First, there's a long code, and then you see the expiry time. So that's just like 1 hour, I think, that you have until this expires. So that's why I think it's safe to show this token. So this token we basically appended to the URL as a query, and then we can directly read it into ArchGDO actually. So if you prefix this VSI curl, then ArchGDO will directly pipe it in through curl from the internet. So we get a GDO dataset back. And it's important to note that you see here the metadata of the file, but it did not actually download any of the data yet, because you can see it's 10,000 by 10,000 pixels, or 11,000 by 11,000. So it is quite a lot of data. And yeah, to avoid having to wait for that to come in, I don't want to download the entire thing. There's only one layer in there, only one band. So let's take it out. And what I'm doing now is, so in this GeoTIFF is what's called a cloud optimized GeoTIFF. And what that means is that it's easy to use a HTTP range request to only download a subset of the data when you need it, so to get only the data that you want. So internally it's tiled up in 22 by 22 windows. So if we pick one, again very randomly, of these windows, then we get the indices that apply. And so we can, if we do get index on the band using these indices, we get the raw data back for only this tile. So this is, it was very quick because it's not much data anymore, but this is the actual data. So one thing that we did lose here is the metadata. So it's just a plain matrix. So it would be nice to maybe integrate this well with, for instance, rosters.jl, because it has more tools to make sure that you don't have to permute the dimensions and rotate it to get a heat map that's not upside down. This, well, maybe you recognize where we are. I think we're right here, right? This is Hotel Caracol. Yeah, tomorrow morning, here, anyone? Right, so that showed how to get some raster data in. Next, I want to move to show a little bit about coordinate transformations. So, like I showed earlier, GDAL uses proj, but we also wrap proj directly. So if you want just a lighter dependency to just do coordinate transformations, then you can do that directly. So here's an example of a transformation that we set up. And so, and this is the source coordinate reference system. So this is the Latlon one. And we're going to project to a UTM zone, which is in meters. And always XY is important to ensure that that is always the order of the coordinates, because otherwise it will depend on whatever the authority decides, and the EPSG likes it the other way around for some reason. So we can transform projects by transform points by passing these along to the transformation, which can be called like a function. And here you can see that you get a different, this is in meters, like the local UTM coordinates. But we can also go back. So I wanted to show in here. So this is transformation pipeline. So you can see it goes to UTM, direction is forward, but we can also inverse the transformation, and you probably guessed it, that now the direction is the inverse of the other one. And as you can see, we can go back to the original inputs as well. So Simon already showed GeoMakie a bit, but I didn't want to leave it out altogether. As I mentioned here, yeah, the package needs more work, but there is also, for instance, the leaflet wrapper available, and that you can use the JavaScript library leaflet.js. But this is a typical GeoMakie plot, where, for instance, the coastlines, they are integrated. And in this case, there's a wrinkled triple projection used. So this is more about going forward, some things that I am excited about myself. So there's the Apache Arrow initiative and Parquet. And Parquet files, they are tables and that are often loaded into memory as Apache Arrow arrays, and these are column-oriented tables. So just like dataframes.jl, all your columns are lined out like vectors. So this is interesting because the way it works right now in GDAL is that you have to iterate over all the rows, and that's not always efficient if you are dealing with large data sets. So that's why I'm interested about this, because of this arrow format and the geo arrow specification. It would make it very easy to exchange data with external software as well, and because the memory representation is exactly the same. So arrow.jl already exists, GeoArrow not yet. I've started playing around trying to build something, but GeoParquet does already exist. Like Martin built that past year. Yeah. So just very brief. I think there's some nice pictures in here on, well, these are the column-oriented tables. And yeah, so this is, if you load them in GDAL, that you iterate over the features, but with Apache arrows, it possibly allows exchanging data very easily between, for instance, QGIS, GEOS, GDAL. So it would be a welcome addition to the geometries that are part of the geo interface. So the last point is to show geodata frames. So this is a package that allows you to read vector data into data frames. So it makes use also of ArchGDAL. So here it's loading a GeoArrow file using GDAL, the latest build. And this is just a tiny sample data set, but these are 2 lines and a missing geometry. Yeah, just to show, and this does the same thing. Yeah, I think that's pretty much what I wanted to say. If there are any questions, now would be a good time. Yeah.
So you mentioned that the struggle to find an image with low cloud coverage.
Yeah.
Just to expand on it, that in Stack actually there are some extensions. One of the Earth observation extension, and it has a property which is called cloud coverage.
Yeah.
So if somebody wants to find a data set with low cloud coverage, actually you have it already in the metadata. You don't need to download the data set to find the cloud coverage. So that's an efficient way.
Yeah, thanks. That's a very good point. So one thing that I didn't show because especially for the model results, the planetary computer stores those in SAR files. So those are also a format that's used for n-dimensional data cubes. But that's not one of the things I showed here. But I'm assuming that would work well with SAR.jl as well as the packages like rosters and YAX arrays. Right. Thank you. Cal, yeah.
I was just, it's a random question a little bit, but I was wondering whether there is anything peculiar to mention about when you're looking at, say, the top of the Earth, say the Arctic. Is there anything particularly different about geometries when we get in this realm compared to the rest of the world, or is it not really an issue?
Do you mean the curvature of the Earth or the three-dimensional the Z values of geometries? So to say.
I'm thinking of the fact that ultimately the lines of longitudes converge to a single point.
Yeah.
So there's a singularity there.
Yeah.
That when you look at something like a GeoJSON file, there's an assumption that I think the polygons are cut at some 1, -1, 180, and then 180.
Yeah.
When you start plotting in geographic coordinates, that's great. But once you're kind of looking from above, things get a little tricky. I'm just sort of, that's what I'm thinking about.
Yeah, so as you mentioned, the GEOS geometries and the ArcGDO, which uses them, so that those are planar coordinates. So it's assuming we are on a flat Earth, basically. There are also other packages that would actually be nice to have available in Julia as well, like Google's S2 geometry that approximates the Earth to be a sphere and to do the geometry operations on that. Yeah, so some of these, actually most of these geometries, they can also be three-dimensional, just in that they have X, Y, Z. But most of these functions, like taking the union, that is basically ignoring the Z dimension and like looking from infinite height, so to say. So it's not really three-dimensional, but people often say 2.5D. Like, yeah. Okay, thank you.
Everyone, sorry. The session, the other session, the 2.2, is a little delayed. So 20 minutes more or less. If you could stay here 20 minutes and then they will come back, and one of the same persons who is doing this session will do the next. Okay, thank you.
Yes.
Okay, hi again to who is online and people that came from session 2.2. Just to remember, for the Wi-Fi, people from this site need to access Caracol Wi-Fi, which password is Caracol 2023, and the people from these other sites, the password that is Hotel Caracol, that is open. We are sorry, so the session 2.2 had a bit of delay because of technical issues. So we'll now give the if you prefer, Simon, you can continue whatever you want. So now we'll have the hands-on session 2.1, working with SAR and in SAR data, with Christian Sorensen. And Christian received his master's degree in Earth and Space Physics and Engineering from the Technical University of Denmark, and has a specialization in Earth observation. He is currently working towards a PhD at the National Space Institute of Denmark, where he's trying to increase maritime domain awareness using satellite data and artificial intelligence, meaning vessel detection and classification, as well as vessel trajectory prediction, with emphasis on the security sector. He's also working a bit with satellite data fusion of SAR data, IES data, RF data, and more. For those who were not in the other session, Simon Lupemba is a junior remote sensing site study in MedSat, working in the scatterometry team, and he supports the quality monitoring, calibration, and validation of operational scatterometer products, and also prototype and maintain processing software for the extraction of products. Okay, thank you.
Thank you.
Let's see if it works. Great. Hello, everyone. To those of you who weren't at our other session just before, we had a small introduction to synthetic aperture radar and also our SAR processing package. And I don't want to introduce all of you to SAR right now, but I just want to say that this is a package that we are trying to implement in Julia, trying to make it a part of the Julia ecosystem such that you can work fully with SAR images in Julia without any commercial software. And this is very much indeed a work in progress, which we started a few months ago. We're looking forward to it being, further developed. So we're looking forward to, ideas and stuff. And on Friday, we will then have another session where we'll talk a little bit about the SAR processing package and where we see it going in the future. Where we also show a little bit more about the package. So so let's get started. First up, I hope most of you or all of you have the notebooks and the data that we'll use. If you used the USB that was passed on earlier today, you should have everything. So in this USB, there are some notebooks and some hands-on session. If you go to the hands-on session, you would be able to see INSAR coherence estimation where you can find our notebooks. If you don't have that, you can also find it online on, if you go to the Air Center's GitHub page, they are hosting the SAR processing package and also the JuliaEO. And here you can also find our notebooks. If you can't seem to get it work, just raise a hand and Simon will walk around and help you while I'm up here presenting. And then, if you did copy everything from your USB, you'll be able to find it in here, as I said, in the package. If you only copied the data from the USB, you would not have our data. Yeah, that doesn't make a whole lot of sense, but that's because our data folder is in the hands-on folder. So therefore, you would need to find the data somewhere else. And you can also, if you don't have it from the USB, you can also download that online. And I will show you briefly where you can do that. So if you go to the notebooks and then to our SAR processing package, and you pick another branch that is called, EO workshop presentation. Yeah, sure. If you go to the EU workshop presentation in our SAR processing package, you can press this link and download the data even. So hopefully all of you can somehow get the data. And then when you have the data, you should then be able to put it in our data folder. How can I increase the size here? Is that possible? I don't know. anyhow, you should have the notebooks and the data in the data folder up here. Command plus. Oh yeah, there you go. Have the data in the data folder and then notebooks there. All right. Again, try to do that while I'm talking a little bit here. Otherwise, raise your hand and Simon will help you. Great. So in this hands-on, we will introduce this SAR processing package, and we'll do it by 4 different notebooks. The 3 first notebooks are mainly just introductory to the package, and like you can see some SAR images, and we look at the ocean, we look at different things that you can see on SAR images, and we try to reduce some of the speckle that Felix mentioned earlier today, and find some objects. And these packages, these 3 notebooks are mainly introductory, and then after a small break, depending on how much time we have, we'll move on to interferometric SAR, which Simon will maybe briefly introduce before we move on to the notebook. Great. Now, if you have opened the notebook, the first thing I would like for you to do is actually to scroll down a bit to where you can install the package. It's down here. In the first cell, install the package and then let it run while I then talk a bit more and you scroll up in the notebook again. So we are installing the packages. It takes a few minutes if you don't have it. And while you do that, I just scroll up again and continue on talking. Right, I'll just, maybe it's a bit too big now. Great. So first up here, we then have a SAR image. If you recall Felix's presentation, he did say that you perform this multi-looking of images. This is one of those so-called multi-looked images. And the reason why we have it is actually just to show some of the features in these SAR images. To the left side of the image, you can see that there is a slightly higher intensity, like right here, compared to the right side of the image. And that is actually due to this radar geometry, where the incidence angles play like a big factor in the intensity of your pixels. So you're often doing some sort of processing to like account for this varying incidence angle. We have not done so here, just to show you that there is a higher intensity on the left side of the image. Yeah, you can also see these dark patches and white patches in the ocean. So this is an island near Japan, and this is then all water. And some patches of the water have a lower intensity than others, and this is due to waves and capillary waves and other locations also rain cells and other stuff. With a rough surface from waves, we have a higher intensity. So this is what we can see here. So we can actually say something about the wind from these SAR images as well. We also see the land has higher intensity because it has there's more scattering, less specular reflection there. We see some high intensity peaks in the ocean. These are mainly ships, and I look for those in my work, and obviously just looking at a ship like in here is comparatively easy actually, and we'll even find one later. If we zoom in on a patch of the image, you can see some of these effects that Felix mentioned earlier today. He mentioned foreshadowing, layover, and all of that you see from mountains. You can actually see a little bit of it here. And we can also see that there is like a side of the mountain have a much higher intensity. So it's quite easy from this image to see that the radar is actually looking from the left to the right because of these effects. And that's also why like radar images is not just regular black and white optical images, like it has a meaning, all of these things. All right. Great. And now to the SAR processing package. So as I told you just before, we are trying to make a package that can like encapsulates all of the SAR processing in Julia. And we started a few months ago, and we are working a few hours on it every week. So we are not that far yet, but we are welcoming area collaborators. And so far we have some, how can you say, SAR-specific processing steps, like the geocoding, the INSAR that Simon will talk about later, the sensors. These are, how can you say, specific for SAR images. And this is where we actually spend like most of the time working on. And then we have like a few other things like object detector, speckle filters, and visualizations. Now, we don't know much about Julia yet. So we would like for people to tell us how we can, for instance, do the visualizations better, because there's no reason for us to not use Makie, for instance. So maybe starting from the hackathon, we'll change this package, who knows? Likewise with object detectors, like these are just made to show something. Currently, we can only use the Sentinel-1 SAR satellites that Felix also introduced. However, in the future, it's quite simple to add others. Oh, simple. We can add others like TerraSAR-X, RadarSat, and so on and so forth, because much of the other things like over here are very similar. And the different SAR satellites are actually trying to make the data similar. So he also mentioned a company called ISI. Their images are built like exact same as Sentinel-1. So we can just add ISI here and everything is the same otherwise. We are not there yet, but like future. Yes, so even though this is what we spend most of the time on developing right now, this is not what people normally use when they use SAR. They use like object detector or speckle filters or something like that. So it's kind of like, this takes the most time to implement, but people don't use it a whole lot. We hope that they will do so in the future, but maybe. But it's really interesting what you can do, and we'll see so later. Yeah. So let's move on. Hopefully everyone now has the SAR processing package and also using plots. So the first thing we'll now do is to load some subsets, because these SAR images, they are also like several gigabytes each. So we have like a few subsets for you. Now here we then see that the subsets are indeed complex. So the SAR images have both a real and an imaginary parts of them. And from those, you then find images that looks nice. So you can obviously from them, if you do like this, we can take the real part and the imaginary part, obviously, and the face. Not a lot of people use, angle. Not a lot of people use the angle of the data, but we will do so in the INSAR part. They actually just use the amplitude of the data. And so will we, in the next 3 notebooks, we'll just use this amplitude image. Now, this is then what we see right here. It's a flipped amplitude. It's a flipped image compared to like, how can you say, lat long, but this is then the radar geometry. And here images, they're flipped because this is how the satellite images. We can see some high intensity peaks as well, and all of the other things that we saw in the other image. Great. Now, then looking a little bit on the image, this was then the amplitude image as I just saw. Now, if you take the square of that, we get the intensity image, and that's actually exponentially distributed. And that's a nice thing because a lot of the applications you do or operations you make on these SAR images have some like statistics. So you need to know about the statistics of these SAR images. And just a single look complex image, as we saw just earlier, is exponentially distributed negatively. We also have these multi-looked images that, yeah? Yes, of course I can. Wait. Yes, wait. Is that enough? Yes. Okay. Now the amplitude image by itself, this is again the intensity. The amplitude image is then not exponentially distributed. In fact, if you look at it, a part of it is Rayleigh distributed. But there we go. This small subset we have right here is one of those homogeneous areas that Felix also mentioned. When you just look at it, it doesn't look that homogeneous, but in truth it is because of this speckle noise kind of thing that Felix mentioned. And looking at that, we can see that it actually has a gamma distribution, which is in some cases rather important. Yeah. Now, this was then just a brief introduction to the SAR images and how we can load them in the SAR processing package. There wasn't anything more on this notebook, so let's move on to the next one. It's the one you have up here called Speckle. We move up, we load it again. We load the same images. Hopefully. Okay, great. Looking at this again, we see in the ocean, we see it's very like this speckle noise that Felix mentioned, and we just saw in the homogeneous areas. Now, just to a brief recap, this speckle comes from the different scatterers within this resolution cell. So a SAR image has a certain spatial resolution. The SAR, the Sentinel-1 satellite, has like a resolution of 3 by 21 meters ish. And within this cell, there are very many individual scatterers that each change the phase of this SAR image. And as we just saw before, this is a complex image with a phase. Now, if we take the amplitude of that, we can see that these different phase contributions are actually changing the intensity of the pixel greatly. Even for two adjacent pixels that are pretty much the same, they can look very, very differently because of this speckle noise. And that's pretty annoying. So we want to like somehow estimate the true intensity and reduce the variance of these homogeneous areas where there's speckle. And this we can do by speckle reduction. One thing that we should note is that speckle is multiplicative, meaning that if you increase the intensity of the pixel, you also increase the speckle. And that's quite important in SAR processing and also in parts of classic computer vision things, because you can't take the difference of two images due to this nature. So for instance, if you have I don't know, some filters where you normally take some pixels, plus them, minus them, whatever, you can't do that with SAR images. You need to take the ratio between them. So you need to know these things when you implement whatever with SAR images. Great. So we want to reduce this noise. And we'll do that by just taking the mean of a region. That makes sense. If we have a big region and they are all the same, we can just take the mean of that region. Again, we have this homogeneous area here that we have taken a subset of, and we want to like estimate the despeckled intensities. We do that using the speckle mean filter, which is just taking a sliding window and finding the mean value of the center pixel for that sliding window. And that should then reduce the speckle. Here we have picked a sliding window of 9 times 9, and you then see this. And that should then be speckle reduction. Let's look at what this is doing for the intensities. So we can actually see that when we are doing this speckle filtering that is performing some sort of mean filter, we are changing the statistics from the gamma distribution to a Gaussian distribution, where we can easily see, I hope, that we are decreasing the variance. And that is exactly what we wanted. So we can see that somehow it works. Now, this was a 100% homogeneous area that I just showed you. It doesn't always work like that. Let's take this region again. We want, obviously, the filter to do this mean filter I just showed you here in the homogeneous area, but not, for instance, here at the shore. Therefore, we implement what is called adaptive filters, adaptive speckle filter, similar to what Felix introduced, but this is way more simple. So here we'll actually try to implement something that is called a Lie filter, that is adapting the speckle filtering depending on the homogeneousness of the region. So if it's a very homogeneous region, we do the exact same mean filter as I just showed you. If it's not homogeneous, you do not perform this filtering. Let's see if it looks any better. Oh wait, sorry. Let's just. This is a Lie filter, and we can then compare them. Obviously, wait, sorry. Maybe we should just see the mean filter first. So this is just the same mean filter performed on the entire image, well, the entire subset of the image. And we can see, yes, it does perform good speckle filtering in the ocean, but not so like here. That's what we want to like do. So therefore, we are implementing another filter that is called a Lie filter. And it's instead of implementing the speckle mean filter, we implement the speckle Lie filter. And here we then can see that, yes, it performs the same mean filtering in the ocean, but not so, for instance, in the city or here at the shore, where it's very inhomogeneous. Now, both of these two filters are very, very simple, and we implemented it just to show them for you guys today. But if there are some Felix or others who want to implement some other advanced filters in our package, you're more than welcome to do so in the hackathon or whatnot. But yeah, that was then speckle filtering. That's it for this notebook. Please, if you have any question or you can't follow along, just, yeah.
Yeah, it was just, this reminds me of a slightly different problem, but in oceanography, we have data that sample a turbulent field.
Huh?
We have data sets, satellites that sample a turbulent flow field.
Yeah.
And so there are regions where there's a lot of noise. Like if you have the Gulf Stream, for example, is typical.
Yeah.
There's a lot of activity there. And so we have similar problems somehow of filtering the smaller scales.
Yeah.
But we don't want to obliterate the Gulf Stream. Right? We want to smooth over the big current. And so what we end up doing, and I don't know if this is useful, is using a diffusion-based operator, which you can make anisotropic. And so if you can, for example, in the case of the coastline here, there are very clear directionality to the problem, right? And so to the extent that there would be kind of a directionality in the data set, you could maybe do a trick like that of like diffusing in one direction, but not in the other.
Yes. So, yeah. So this one is actually, this is just called the Lie filter, simple Lie filter that we showed. There have been built upon very many extra Lie filters, Lie sigma, Lie whatever else. And one of them is actually making these masks and figuring out what direction should we filter in. And it's kind of doing that. But yeah, there are, I mean, I don't even know 5% of all the speckle filters out there. So it could be that there is something like that. And yes, we want it. So you can also just, if you want to. But yeah, for sure. Otherwise, we'll move on to the next notebook, 3 object detection. Wait, what time is it? Oh, great. Yeah. Again, seeing the exact same image. So I'm working with maritime surveillance here under also ship detection. That is generally also part of object detection. So therefore, it's pretty neat to find objects at sea. And in this notebook, we'll like try to implement one of the simplest ways to find objects in these SAR images. And that could, for instance, be that we have the same image here. We want to extract this little patch we have right here to determine, is this a ship or is it something completely else? In this notebook, we won't classify it, but we'll extract this exact patch right here. Obviously, it's the object detection that we use right now is kind of redundant in this day and age with deep learning, where you're using those to find them, but somehow you need to make the data set. And I've used kind of like this method to make the data set for deep learning. So this is still pretty neat and good. Anyways, we'll use a method called constant false alarm rate, abbreviated as CFAR. And what we do here is actually just to, we are comparing the statistics of a region that we are interested in, region of interest, and we are comparing it with the statistics of some kind of cluttering or background ring, or call it whatever you want to. And if the intensity of this region of interest is much, much higher than this clutter ring that we are looking at, we are saying, yeah, there is an object there. We're not saying which object, we're just saying there is something there. And then you can obviously vary the size of both the clutter ring, the region of interest, and the guard ring that you are using to make sure that these things are not overlapping. Yeah, and then if we move down a bit, we can we then have it here where we have like a target pixel. We have the target pixel that we are looking at, and we are comparing it to the mean of the background ring plus the variation multiplied by this t, which is then defining the threshold. I don't want to go into much detail about that, but it's pretty much just you find a threshold. If the intensity is higher than that, it's an object. So we are defining the sizes of these different parameters. And then we're trying to implement it on our image. Let's see what's going on. Okay, so we have found a bunch of different objects. Now we have a lot of noise mid-sea, as you can see. And then we have a lot of objects on land, which we obviously expect because there's a lot of man-made and different types of objects. And then we can see two, maybe let's zoom in a bit. No, it didn't work. Okay. Okay, well, right here we can see two like very high intensity peaks, which are a bit, higher than these. And these then correspond to the two objects that we found that we could clearly see in the original image. But also we see that like there's a lot of objects here. So there are obviously better ways. And a simple one is just to perform some quick and dirty operations. And one of these is another type of CFAR called convolution and pooling CFAR. Honestly, it's not that this is the best. It's just something I took from an article. We took from an article where we're just trying to find some edges first and taking the average and then performing some morphological operations to see what we can do. Let's see what results we get. Now this looks much neater, much nicer. We still have all the objects on land, which is expected using this method on land. But we can see clearly these two peaks in the ocean and all of the others are gone. We then want to take these objects out and look at them and to, for instance, classify them or use them for whatever. Oh yeah, we could, if you want to, you can afterwards try to do the speckle filtering before and see if that reduces the number of these objects in the sea. But otherwise, we'll just find these objects. This function is actually just going in and finding the center position of the object. And and then we are just plotting the positions of the objects to compare the different methods. So here you can see the one with the morphological operations, found objects all of these places, and yeah, the other one found all over. So yeah. So now we want to look at these two, or extract them and look at them. Well, or at least one of them. We do that by just extracting the index of the objects and plotting it. So this is then the object we have found down here. We have a subset of right there, and this is just a random subset. And this we could then use for further analysis if we so wanted to. Yeah. I don't know if it was a bit too fast, but that was actually it. That was the brief introduction to the package and like a small general introduction to how you can handle it. Yeah. Question down there? Can you wait for a mic?
I'm looking at subset and subset 2. Did you have to these are the two objects that are outside they are offshore, right?
Wait, are you talking about the one we extracted or the images in the top?
At the bottom.
Yeah.
At the bottom. These are the two objects that are offshore, right?
Yeah.
How did you know that subset 2 was index number 50? Did you manually check it?
Yeah, like this was just so the one we subset 2 is just this is not the for sure. This was just a picked one.
Oh, so
this is a random one, and
so
this one I then
one.
found by finding the one with the that was in the bottom of the picture. So this was
okay.
nothing fancy there, actually.
Okay.
Normally, what you do instead of doing it like this, if I want to extract images, I would put some auxiliary data on the image, and then I would find an object, and if it's really close to my auxiliary data, I would extract that object instead of doing it like this. But
okay, I see. Thank you.
Yeah.
I have another question, probably still related to notebook 2, where you mentioned that the noise is multiplicative and not additive.
Yeah.
And then to reduce the noise, you use the mean filter. So is this a geometric mean where you multiply it in a given window, or is this an arithmetic mean where you sum it? So I did not. So it looks a bit.
So it is like you just have a. It's a convolution pretty much you do, where you just take the convolution and take the mean of that entire window.
But when you take the mean, you add things, and I thought.
Yeah, and you're changing the entire statistics of the image. So that's what we showed by you change it to a gamma distribution even.
Maybe I can also explain that.
Yeah.
So for speckle areas, the average metric mean of a homogeneous area, the intensity in the homogeneous area is a estimator for the backscatter. So if you want something that converges to the backscattering, you should take the regular mean of the intensities, and then it will converge. It should converge to the true backscatter value. Yeah, and a common mistake people sometimes do when they do SAR processing is it's very normal to do a log transformation before visualizing the images, and some people also then you can easily end up trying to apply your speckle filter to the log transformed image, and then it does not converge to the true backscatter value of the homogeneous target. But I think there's many articles out there on the statistics of speckle.
Yeah.
question about object detection. How did you actually define these 4 parameters: background window, guard window, probability for alarms? How to define these parameters?
Trial and error.
Okay, so you're just playing with them, and
I didn't play much with them because this is a method where it's genuinely trial and error. You can use them if you know that you're looking for ships.
Okay.
Let's say the sizes can be picked such that you know, like, then your guard window you should ensure that your guard window is large enough for you to be outside of how big a ship could be.
Okay.
For instance,
yeah.
so if the largest ship is some 100 meters long, so your guard window should be large enough such that your background window is further away, in a sense. But otherwise, it's much trial and error. This is not the way that proper object detection should be implemented in SAR. This was just to show that you could do object detection. But yeah,
thanks.
Unless if you know something specifically about the objects you're looking for. Cool. In that case, I'll leave the floor for Simon. Great.
Yeah, so I'm here to go through Notebook 4, and Notebook 4 is about INSAR, and just briefly to recap what INSAR is. It is that if you have 2 SAR images over the same location, taken from like approximately the same angle, then you can derive information from the face. So actually, Christian showed earlier. I'll just step a little bit through this. There's some helpful function to load all the data. Yeah. So Christian talked about earlier that the image, the pixel values are complex, and for most use cases, actually the SAR images you download from the providers are not complex. You download already pre-processed images that have been multi-looked a bit, like combined a bit, and converted into intensities, because that's what you're after for most purposes. But when you want to do INSAR, you're combining 2 or more images and looking at the phase difference. And to do that, you need the original images. Yeah, and here we have taken a test image over a location in the US. I think it's near Boulder, Colorado. And actually, just to say again that we're working with this is a single look complex data from the Sentinel-1 satellite, and it has some features. For example, here when I'm showing the image, I'm only picking every 4th pixel in the range direction, and it's because when you work with these raw data, the resolution is 4 times better in the range than it is in the other direction. But to visualize it makes much more sense to look at a picture where the pixels are more square shaped, because yeah, if you don't have it just stretches out. The image. So there's several different steps in computing this complex coherence, which I will try to step through. And yeah, some of it is to illustrate like what is the process and what's actually needed. And it's based on some Julia scripts that I made earlier together with IQL for computing this in Ferrogram and a complex coherence INSAR. But we're now with SAR processing trying to turn it into a package. It's far from done. So we think there's a bug somewhere in here. So actually the result in the end is probably not exactly correct, but we hope to like get this. We believe we can find this bug soon, and then also to clean up the library and wrap up some of these steps in more accessible methods and have a nice API, because right now there's not like one method that you just call on 2 images and then you get the complex inferogram. So here we have the image. I think it's always good to just briefly what we see on the image. I won't go hard, but here we have some really bright areas and some dark areas. That's the shortening. So that's often some mountains or some hills. At least that's a lot of topography. And over here, we could also have something that could look like topography. Here we have some straight lines, which are really dark. When you have straight lines that's dark, it's often either tarmac or channels. But looking at like how this is oriented, this is an airstrip, an airport. So I think it's 3 runways. And here we probably have what could be some sort of small city. And this, I think, is some circular fields or some circular tanks. It's definitely something circular. So the first step to make the hard step to make in SAR coherence is to take two images and then resample the pixels so they are exactly on top of each other, while conserving the spectral properties of each image to then actually compute the inferogram and the coherence. So computing the inferogram and coherence is quite easy after that. And to do that, we first actually need to have some information about the satellite orbit. So the first step here is to load a file containing the orbit, which is recomputed a while after the satellite has flown to get like the precise position and location. So this is just a time, and then we have a position in XYZ of the satellite and a velocity. We need to be able to find the position of the satellite for all the time in the image to geocode these pixels. So therefore, we need to make an interpolator. The interpolator is not so fancy. It's actually just a polynomial base. I think it's a 4th degree polynomial. And I just visualized the velocity of the satellite during the time it takes the image. As you can see, because the time frame it takes for it to take this image is so short, then the velocity only in the z direction, it only varies slightly. And this is actually how it varies across the entire image and not just the subset. So the interpolation doesn't look so advanced. Maybe I should also say that this here in this first part, it's just a subset of a larger Sentinel-1 scene. So like the way that ESA releases pictures is in this folder where there's actually 3 SWATs, and in which are a file each. And in each of these files, there's like several bursts. So there's a part of a image, and then there's some black pixels to divide it. And then there's another part of the image, and these bursts overlap because of the way that the satellite retrieves these data. So it's yeah, it's a bit hard to keep track of the offsets, and this is also why we probably should try to implement offset arrays for this, because yeah, there's a lot of indexes to keep track of. But we have the orbit interpolator, and yeah, then I just found the airstrip here, zoomed in on that, and the position is around index 450 and 6,500, and we can use the package to transform this position in the image to coordinates. So this is an important step in like resampling the pictures and getting them on top of each other. Yeah, you need a height to do that for the pixels, and I just put in a guess of 10 meters, which is not right, but it's right enough to show the example, because then if you take these coordinates and open this link, then you should come to the site, if the internet is working. Yeah, so we see it fits with it being an airport of some sort near, and this is probably the city we can see on top of the image, because the views are flipped due to the geometry, and we also have some circular fields here. But the thing is, I don't know when this image is, maybe from 2000, and is it from this year? No, I don't know what. I know that the Sentinel-1 image is not a new one, so we have an image from 19. So it can be that there have been some differences, but there's still an airport, so so far so good. And I should also say we have chosen this area because around this area there should happen an earthquake between in the test data we have, in the example data we have 4 images, and there should happen an earthquake either between image 2 and 3 or 3 and 4, but we haven't really gotten around to visualize that yet. So I don't know if you're able to see it, or if it's in this subset that we cropped up. Yeah, so we have the airstrip, and maybe just to say like a little bit what is happening under the hood to find this position. It's actually a system of 3 equations that is solved iterative to find the solution. And the equation is just that the distant, so first of all, each index in the satellite, it can be transformed into a time, an azimuth time, like a time in the flight of the satellite, and then also into a time delay of the signal using some metadata, and the delay of the signal corresponds to range. So you get the when the satellite were flying over this pixel, and you also get how far away the pixel is. And then it's just a system of equation that you have to solve with an initial guess. And it is that the line of sight should be perpendicular to the velocity, so it looks straight to the side of the satellite. The distance to the point on the ground should match the range position in the image, and the point should be at the height above the reference ellipsoid. You solve these equations, you get the latitude and longitude of the point. And we can also go the other way, where you have the coordinates of on ground, and then you transform it into the SAR image. And here it works by you first give it an initial guess of the satellite position, maybe just in the middle of the image, and then you can compute the different the line of sight from the satellite to the point on the ground, and you can compute the angle between the line of the sight and the velocity of the satellite. This tells you if the point is ahead of the satellite or is behind of the satellite. And what you do is, based on this information, you make a new guess in time, and you continue this until it converges, and you have the time that the satellite were flying perpendicular to the point. And when you have that, it's the range is simply just to take the distance to the point. In this example, with like converting back and forth, I just make a rough guess of the height. That is not good enough when you're doing INSAR and you need to co-register these images. You need to have either you need to have 3 images, and then you can do some trick where you derive the height and get the coherence, or you get a digital elevation model. It could also be kind of nice to implement use JuliaGeo or another high-level package to handle some of this digital elevation model. But here I have a digital elevation model covering the area plus much more. Actually, I'm not completely sure where in the digital elevation model the area is, but we can get the coordinates for the digital elevation model, and then just I'll just start by filtering it to only get the ones in the image, and then we can transform it using the same equations as I described before to positions in the SAR image. Once we have the positions in the SAR image, just to say, so for INSAR processing and like for processing in general, we don't need to have the heights of all the pixels in the primary image. If we just define a grid in the primary image and get the heights for those points, we can always interpolate it if we need the heights for the other points. We don't need it for all of that. So we just start by defining a grid in this SAR image. So this just defines a grid that we'll be using, and then we can interpolate the heights to that grid and show it. And this SAR to gray, it's just a wrapper around the Image.jl gray type, where we just, we make sure to map the values between 0 and 1 before. We have been using this a little bit instead of heat map because the images.jl, we think it just makes pretty images, and that's also something to take away. Did I miss running a cell, or is it just a bit slow? Maybe it's because there's something that needs to be compiled. But yeah. So, but in general, we do this because we need to get the heights of the points, and I can already start talking a little bit about the next step. Once we have the heights of this grid, actually the steps are that we convert this grid to latitude and longitude coordinates, and then when we have the grid in latitude longitude coordinates, we can convert it up again to the secondary image. So we have it in secondary image geometry. And then we have the opportunity to resample the secondary image. And so they're stacked completely on top of each other, and use it. Okay, so here we have the digital elevation model for the grid in the SAR image. And what we visually can see is that it looks like it makes a bit sense. We have some mountains here, like some height here, and it's kind of a valley in the middle. And we also have some topography in the right side of the image. Yeah. We convert this down to latitude, longitude. And this actually, yeah, so it tells us all the grid points, latitude and longitude and heights. And this can be, yeah, so first of all, the heights are 10 meters, which is definitely not a good guess for the heights, because, okay, now it's also, I think it's just one side of the image I did. So at least the elevation here is about 1,000 meters. I'm not sure what it is here, but 10 meters is probably not the best guess in the world. But that's also why you use the digital elevation model. It's to get the height. Having this, we actually a good way of we would be able to now resample the SAR image to a coordinate grid, a regular coordinate grid with latitude and longitude, and work with it in nice packages like rasters.jl. And this is very tempting, but for INSAR purposes, this is not good, because it introduces an extra error if you resample both images to a latitude and longitude grid and compare them there. It's better to just resample one of the images to the first image's SAR geometry. So so for now we just keep the points. Yeah. So now we are here getting to the second image. Or maybe do you have any? Maybe you have some questions, but do you want to ask any questions now before we continue with how we handle the second image? Okay, then we just continue, and then if you have some questions, you can also ask them in the end, because maybe it will make a bit more sense when you see some of it. So the second SAR image is loaded here. I've cheated a little bit and visually found the burst in the second image that kind of overlaps. And here you can see, like, actually, so the secondary image is a little bit larger, just the way I selected it. So it also has the beginning of the next burst in it. The reason why we only gave you like a subset is, like, if you take the entire images of the four subsets we provided in the data folder, they fill 32 gigabytes, and we didn't want to pass 32 gigabytes around on a USB. So that's why we made the subsets. But yeah, here we have the second image. We can see it kind of looks similar. To get the grid in the second image, we also need to create an orbit interpolator for that. So it's the same procedure. And now we can transform the grid from the first image into positions in the second image. Yeah, so for example, we have that column, a row 190 and row column 8080 corresponds to this row and this column in the secondary image. So this is the position in the primary image, and this is the position in the secondary image. Now I've written a note about offsets, and this is because the way this row is implemented, it is that it calculates the row using the time and how far the each line, each row in the SAR image is spaced in flight time of the satellite, and so it doesn't correspond to the actual index if you were to take the entire image index into it. So it corresponds to the index if the bursts were not overlapping. Yeah, so in that sense, there's an offset that needs to be accounted for of 503 pixels. Yeah, then now we are almost ready to resample the second image, but there's one more step. There's always a step more, and not always, but in this case there's. And this step is something called deramping, and it's because the way that the Sentinel-1 image is acquired, it is that the antenna is actually scanned a bit during the acquisition. This introduces a phase ramp. We need to remove this phase ramp before resampling to not mix up the spectra of the data. And then we would have to later on add the phase ramp corresponding to the primary image before comparing them. So first here we take the secondary image and we remove the phase ramp. So it's phase ramped, and now we can interpolate it. I should maybe say for interpolation that SciPy interpolate is maybe not the best one, but the reason why we just started using it a little bit is because we could not find any alternative. The heights, when you interpolate the heights in the first step, the heights are unstructured. They're not on any kind of grid in the primary SAR image. So we needed to have an interpolator that handled that, and SciPy provides that. But for this, I'm pretty sure that we could use Julia Interpolate because now we're interpolating on data from regular grids. So we find all the positions that we need the image in the second data from, and we create the secondary image, and we create an interpolator. And now we're ready to interpolate it. This takes a little bit, so just put it to run. But what we do is that we just resample the secondary image, so right on top of the first image. And now I can also talk a little bit about something I forgot to talk about earlier, or like just didn't mention. Again, most of the time you would not get the complex, download the complex, or it already resampled. Did it? Fast. Okay. So most of the time you wouldn't use the complex images. You would just, if you are interested in the intensity, you just download some more preprocessed to start with. These intensity images, they're actually we don't calibrate these images, so there may be some artifacts due to the antenna pattern or due to the different sensors. When you do the INSAR estimation, you look at a local window, and then you compare the phase difference between the value, and for the coherence, you also scale it with the magnitude of the images. So in that sense, for creating the INSAR, the calibration part is less important and can actually also introduce additional errors if it's done wrong. But if you were to use this for for comparing like backscatter intensities, you would have to go into the metadata, find the right value, and compute some calibrations. And also, even if you wanted to compare the backscatter values in these areas with topography, you also needed to do some corrections for that. Just to mention it. Okay, we have the resample images, so we can just plot them on top of each other. And here I just map it to red, green, and blue to show it. And we have the secondary image as red, and the other images as green and blue. And you can see there's some structures coming up. I don't know. Do any of you have an idea what you can see on this? Okay. So first of all, we have something a strong scatter appearing here. So that's quite clearly that in the first image, the primary image, so there was like nothing much here, but then there comes something apparent. Something happens with these fields. So for some reason, these three fields were stronger in the first image and then are less in the second image. And that can be either due to some vegetation change or actually some harvest. We have a general very bluish color, and that can be due to two things. First of all, it can be due to the missing calibration, because actually right now we're comparing images from two different satellites. So we are comparing images from Sentinel-A and Sentinel-B. So that's this calibration part. Another explanation could be that it's dry during the second image, but more moist and wet during the first image. Soil moisture have a large effect on backscatter. So if you have a target that is dry, it will give less backscatter than the same target when it's more moist or wet. So that could be a thing. You would have to calibrate the images to be sure if it's the second explanation of the first. Yeah. Okay. Now we re-ramp the secondary image using the phase ramp of the primary image. In this way, they have a phase ramp that matches, and we're able to compare the phase. The phase part. Yeah, and we have a part more. So before comparing the phase part, there's a part of this phase range between the images which we know already and is quite obvious, and that is that between the two acquisitions, the satellite is not positioned exactly at the same point. The satellite during one acquisition is have a slightly different place on the sky than during the first, and this results in a difference in range. But this is a difference in range that we can compute, and we can use this difference in range to kind of subtract the phase changes that are due to the movement of the satellite. Because what could be really nice to have left is the phase changes that are due to movements of the ground, not of the satellite, because we know the satellite moves. So here we can create a synthetic inferogram. So this is synthetically how the phase would change if the only thing that happened was that the same scene was imaged by the satellite from the slightly different position. Here we have made our own like homemade plot color map where the phase goes from blue to red. and then we made an image. And like you can also make these images in black and white, but for some reason, people working with INSAR really like they really like these colors. So so we try to to make the same colors so it doesn't look too different. Yeah, and now we are ready to plot the phase difference. So this is the phase difference between the two images. We have the primary image and the secondary image resampled, and then we remove the part due to the flat due to the satellite change. And here we get an inferogram out that is probably wrong. I think that we believe there's a bug somewhere in the code that creates this. But first I will present it's correct, and then after I will explain why I think it's wrong. So what we see here is we see that some areas, for example, the fields here, they look noisy, and that is a good sign because you expect areas where the surface is not stable, like the surface structure change between the acquisition to create random phase and create noise. So if you have these fields where there's vegetation or there's harvest or something, that would destroy the signal in the phase difference and create noise. So that's good. The phase difference here would corresponds to changes in distance from the satellite. So here you would have that from each of these, you would have that this means that all the scene kind of moved vertically up or down. I don't know. I would have to make a color bar and analyze it a little bit more to get out. But this would correspond to the whole scene had moved between the two acquisitions. The reason why I think there's a bug here is that all these lines are really they're quite a lot in the range direction. Like, so you have a change here in the flight direction and not so much a change in the other direction. And there's a lot of them. So it looks like something really moved. I think this could be due to a small error in the resampling or in the orbit interpolation, because errors in when you so if you miscalculate the satellite positions a bit or you mess up an index, it can also look like things have shifted in range. So that could be an explanation, but to really I think our next big step for this is to make this a similar inferogram using some commercial software, so we actually know like what is to be expected of this scene, and then we can go back and debug the individual steps to find out like where this slight change occurs. Yeah, and so actually, so this is just for individual pixels. Normally, when you analyze these inferograms and the complex coherence, you use a sliding window to get the complex coherence, which is a measure of how stable the surface is between the two acquisitions. So here we have a image of the complex coherence, and here we see very clearly that these areas here are very unstable. Like there's something in the surface that changes, like not a constant movement of the pixel, but a change of the surface within the pixels. We see that the airport, we don't see the airstrip now because the airstrip is actually quite a stable scatterer. Yeah, the phase of the complex coherence, it looks like the plot I showed before, just filtered. Yeah. So this is the complex coherence, and it's also, it could be expected if you have a lot of movement in the image, but yeah, we will have to analyze it further. So this is it for the notebook, but I think first of all I would take questions, and second of all, so this is, there's 4 subsets in yeah, there's 4 subsets in the data folder, which is provided to you, and right now we just made the complex coherence between image 1 and 2, but you can do all the combinations of these images, and you can also change the ordering if you wanted to play around with it. You can also try to, so the grid we did was quite coarse, so if you want to try, you can also try to make a more fine grid in the geocoding and resampling part to see if that improves something. Yeah, so in that sense, we have some more data that you can play with. You should know that yeah, InSight requires a stable surface. So the more time difference there is between images, the more you would expect the general coherence to decrease, and the more noise you would have in interferograms. Yeah. So any questions? Yeah.
Can you go back to the place in the notebook where you showing the both images, one in green, one in red?
Yeah.
Okay, so about how to interpret this image. My question is, in the red points, is there something added or is there something missing?
So the red, let's see, the second image is shown as the red. So here there's something appearing in the second image, and the second, yeah, so there's something added.
Uplifting, right?
No, so this is here. This is the intensities shown. So this is doesn't correlate with ground movement, but with the backscattering. Okay. So this goes from there's nothing scattering the radar light back to there's some structure or something that have appeared, okay, that scatters it back.
Okay, so that could be caused like deforestation, for example.
Yeah, yeah. I think this is very clear. So I'm not sure what this is, but and it's also been a while since I interpreted SAR images. But it being so strong, it looks. I would expect it to be. I don't. It's kind of a hard. Maybe is it a landslide? It could look like a landslide. I think it's before the earthquake. But it could be something like a landslide, drastically changing how that small part looks from one image to another, because it looks too big to be a building that's just put up between the two images, or some other strong. But it's yeah, there's something.
Okay, thank you very much.
Yeah, I was just trying to speculate as to what those circles are, and do you think they are water tanks or something like that?
I see. it's like, I think it's circular fields. At least on Google Maps, it looks very green.
Oh, I
But
see. Okay.
yeah.
So
So
that's they've been.
yeah, I think they've been harvested. That could be a really good one. At least the three top ones. It looks like they, because what you have with
Harvested or grown at different rates, right? The vegetation might grow at different rates.
yeah, but I think actually like a newly harvested surface could be, if it's not too rough, it could scatter a lot of the light away. Because the thing, if it's due to growth, then it's also like, why is it not happening in these two? Because they have quite high, but it could be different crops. Again, I think Felix is the expert on land classification. I think he has a comment.
Yeah, it could also happen that you have different watering schemes. So it could be that the top fields are watered right before the first image and then drying up and then therefore reducing and backscatter. But I mean, it's something that we can only speculate about.
No silly question.
Just wanted to confirm if it's already possible to access to Sentinel-1 data through the Earth Engine data catalog, or do you have to have the images a priori to your
Yeah,
script?
so for this spec, we have not made any functions to download the data automatically. You have to. That's also quite annoying when you work with it. So right now you have to get the data from the image from one source. You have to get the recomputed orbit from another source, and then you also need to have a digital elevation model that covers the area. And you need to find these three things and make sure they overlap. It would be really nice to implement some utility data get live part that could like help ease like downloading some of these data, retrieving like at least something like the digital elevation model. It could be nice. Just I think there's some in raster. Yeah. So I think to implement something like that would it will not improve the quality of the inferogram in the end. Like if there's an error there, there's still an error, but it would be make the user interface much easier to work with.
Thank you.
Sorry to put you on the spot, Simon, but is there like a roadmap for future development? Something that we can count on using at some point?
Like so, we
It's
have
fine
a
to say no, right?
We have a presentation on the roadmap and vision on Friday. So so we will have made a roadmap very soon. But the first part of the roadmap is to actually is not to like expand the functionality scope. Like the functionality scope is not so big, but the first part is to get some validation data to see if it's correct, and then also just to clean up and improve what we have now. And like we also like, I don't know if you notice in the notebook, but like none of the functions are exported, so you have to do SAR processing dot for every function. So it's also because we didn't want to decide which functions to export yet. So that's like a part of that. But yeah, there will be a presentation on Friday. We will present more.
And maybe the hackathon later can start that conversation.
Yeah.
Just a suggestion, a comment. Do you know the package satellite toolbox? It is,
Yeah.
okay.
No, I heard about it. So the thing what's your suggestion?
Yeah, I was wondering if you really need to interpolate the satellite position. If you cannot, maybe you can compute it actually.
Yeah, so I think actually, as I showed here, it could be a good way to validate if it's wrong. But the thing about the polynomial interpolation is that it's the variation in the velocity is not so great, not so big. And if you interpolate it with a polynomial, you can evaluate it really fast. Where if you need to propagate an orbit state, it may take some more time and some more complexity. But I think also depending on like what your data source is, like so I don't know how ESA makes this data, but I think the precise orbits that we download is actually ESA that have some precise orbit states and then interpolate, propagate them themselves using an orbit propagator. So I think they have done part of that work. So we only have to interpolate, but it definitely could be an idea to try with that, and also it might be necessary if you consider data where you don't have that many orbit states. So if you get data from another data source or satellite, where you just get like a couple of really precise orbit states doing an orbit, then you would have to propagate it to the position to locate it.
Concerning this figure, I was wondering what is the unit of the vertical axis? Is this?
It's meters per second. Yeah, it's meters per second. So the speed of the satellite is around 7.5 kilometers per second. So in 1 second it flies 7.5 kilometers, but that also means that in 1 millisecond it flies 7.5 meters. And that was actually so to start with, in implementing this package, we started by converting like the time units using the datetime library and to time differences. But we really fast discovered that when you're dealing with the speed of light, milliseconds is definitely not good, because that's not the accuracy you want. And then I think the dates also support some nanoseconds, but in the end, what we actually did was that we when we load the SAR image into an object, we give it a reference time. Yeah, we give it a reference time, and then we use all the time we have in as floats, which represent like seconds, because to have the float accuracy and also to be able not to have to round to integers. There could probably be a better way to handle it, but this was how we did it in the script, so we just started with that. But to have a good object for the times would also be nice, that both that supports the time ranges you need to work in when you're timing a radar pulse.
Just a quick follow-up on that. I'm not sure it's been mentioned, but it's very useful that there's a website called JuliaHub where you can search for packages, and since they're all registered to the same thing, you can find them. Especially for when you know what you're looking for.
Yeah.
If you type satellite, this one will did come up for me, and I just meant to mention it for those who might have never seen Julia Hub. It's a very useful website.
And like if someone finds a bug like and suddenly you have a nice infogram with like less fringes, please tell us because we will be very happy. But otherwise, we will try to find it ourselves. Yeah, I don't. I think this is like you're welcome to continue to play around with the package, or you're also welcome to. I think maybe the hackathon you can get the source code and try to add some features or wrap some of these things up. Like I mean, there's so much you can do. There's so much that needs to be done with this package, so there's plenty. But otherwise, we will also still be here. Yeah, thank you for listening.
Okay. Well, at 3:40, we'll have a coffee break until 4. I please ask you to, everyone who is here at 3:40 would like to take a group picture outside whenever we go to the coffee break. And then at 4, we come back to the hackathon. Okay. For those who are assisting online, thank you for being with us today. We're now closing this session and we'll see you tomorrow. Thank you.